I find it very helpful to think of quantum field theory as about data sets and about signal analysis. Whether that comes to an explanation or not, I'll leave to you to decide. So I'm doing this as part of Curt Jaimungal's competition for outstanding research explanation. It will be quite long. It will be over 3 hours, and so it's kind of the equivalent of 4 lectures. Now, you'll find a common story is that quantum mechanics is incomplete. And so people try to add to quantum mechanics enough that it looks more like classical mechanics. But I think it's a more interesting game to think of quantum mechanics as complete in the rather limited sense that we can encode all the data we get out of many, many experiments into Hilbert spaces because we're encoding a finite amount of information into an infinite amount of space. That's a very limited sense. On the other hand, there's a sense in which classical mechanics is incomplete, and that is because of the no-go theorems such as Bell inequalities, Gleason's theorem, Cauchy-Specker paradox, and so on. But I think a consequence of that kind of approach to what the relationship is between quantum mechanics and classical mechanics is to ask what it needs, what we can add to classical mechanics so that it is as complete as quantum mechanics. And I'll show you that there are just two things that have to be added. And we can use, first, the full power of the Poisson bracket to add generalized probability and measurement incompatibility, non-commutativity, interventions into classical mechanics, making it more powerful in that sense. And the second thing we have to add is an idea of quantum noise, because now we're thinking classically, more classically, I should say, we have to distinguish quantum noise from thermal noise. And the distinction I will show you is really quite clearly the difference of Lorentz invariance between them. Now, once we have constructed this CM plus that is as powerful as quantum mechanics, then we can describe any experiment using whichever we think is more convenient. Different descriptions of an experiment don't change the results in the data sets. This is just a matter of what we say about the experiment, and the experiment really doesn't care what I say about it. I can curse it or whatever. Now, there is also an opposite game. We can look inside quantum field theory in particular and find a classical stochastic field theory within it. And I'll show you in particular how, for quantum optics, there is a commutative, what I'm going to call QND optics, which is a terminology that comes from quantum computing, quantum information literature. QND optics, quantum non-demolition optics, just means, in fact, commutative instead of non-commutative. Now, I haven't mentioned signal analysis before this point. Signal analysis is helpfully between classical mechanics and quantum field theory because signal analysis is about signals. It's specifically not about particles and their properties. That is something that also quantum field theory is not in the first instance about particles and their properties. Signal analysis also already uses Hilbert spaces, just because it transforms between different coordinate systems when it uses for analysis, and there's even the idea of Heisenberg uncertainty principle is implicit when we do time frequency analysis. So the first half of this talk will largely be about ordinary quantum mechanics to establish a framework within which quantum field theory will look more natural. And specifically, we'll focus on algebraic quantum mechanics. First part, though, first 10 pages or so will be less mathematical for the most part. We'll just be trying to establish why it is worth thinking of quantum mechanics and quantum field theory as about data sets and about signal analysis, and specifically, again, not about ensembles of particles. After this talk, you can go back to thinking in terms of particles. There's no reason to disdain them completely, but it's worth just backing away from them and seeing what it looks like if we don't talk about particles at all. So part of that, we have generalized probability. There'll be 2 slides which are slightly more mathematical. Then I'll talk about the two-slit experiment in a kind of field theoretic way. But then we'll go into slightly more mathematics, where we'll discuss algebraic quantum mechanics, which is slightly different from the way you usually will learn quantum mechanics. You can find it in literature, but not very easily. And that we do because we can similarly discuss classical mechanics in algebraic ways as well. This goes back all the way to 1931, where Bernard Koopman introduced the idea that we could have a Hilbert space formalism for classical mechanics, which would then parallel quantum mechanics. That is something that I'll discuss on just one slide. Then I'll show you how classical mechanics we can make into CM plus really quite explicitly by using the Poisson bracket and by introducing quantum noise. Now we have, for the measurement problem, because we've now introduced non-commutativity into classical mechanics, into CM plus, there will be a measurement problem for it as well. So that will help us understand the measurement problem for quantum mechanics as well. That will lead us as well to an idea of what I call the super-Heisenberg picture. Instead of the Schrödinger picture or Heisenberg picture, there'll be the super-Heisenberg picture. I'll leave until then, until slide number 25, before I'll show you what that is. Then for Schrödinger's cat and for Bell inequalities, I'll discuss both of those in rather field-theoretic sort of ways as a kind of introduction to the second part of this talk on quantum field theory, which I'll discuss mostly as a signal analysis formalism, mostly not in terms of data and data sets, really staying in quite an idealized sort of approach to quantum field theory. Because we'll be thinking signal analytically, renormalization looks a little different, I've found. And in particular, it suggests an axiomatic kind of nonlinearity that can be added into the Whiteman axioms in particular. And for the Whiteman axioms, we have the Reeh-Schlieder theorem, which will indeed justify that nonlinearity as an approach that is equally powerful as the ordinary Feynman diagram approach to interacting quantum field theory, for example. So that will allow us to rethink interacting quantum field theory. So now we'll head into quantum gravity. We'll be using what we've just learned about quantum field theory and how to rethink interacting quantum field theory. And well, you will see for yourselves whether or not that is at all compelling. Part of that will be to find that it's useful to think about quantum gravity in terms of quantum non-demolition field theory. In other words, in terms of CM plus as a classical way to approach quantum theory, and hence to allow us to integrate CM plus and ordinary gravity together. Now, I'll just have one slide about quantum computing. Not a lot. I shouldn't say a lot because I don't know a lot. Nonetheless, the kind of story that I'm telling here in the slides before that do give us a slightly different perspective on what quantum computing might be about. So none of this is about a theory of everything. What I'm trying to do is more to analyze the mathematics we have so that someone else can create a grand synthesis. All of this, much of this is published. The discussion of renormalization and so on is not published, but can be found on the archive. So this is a rudimentary schematic of an experiment. We have a region of space and time we want to know something about. And so we surround it with many devices, each of which is connected by a signal line to a piece of hardware that analyzes the signal out of each device, which characteristically might be relatively close to a zero voltage, for example, but noisy nonetheless. But at a certain point, the voltage suddenly jumps to a much higher level, and we can identify that and go and find out from a clock what the time is, record that time, send it down a data line to a computer, which will record that experimental data, that digital data, into computer memory as a long list of such times as a data set. Months or years or seconds later, we'll do a data analysis, which will result in us writing a paper and so on. Now, from an engineering perspective, there's a rather characteristic sort of event here where we convert the analog signal out of this device into a digital format of some kind. So this is something that happens only once. This is not something we can move around by fiat in quite the same way as we would move the Heisenberg cut from one place to another. Nonetheless, so in many ways, what we've done is we've isolated here as being the place where the measurement happens from an engineering perspective. Nonetheless, we know quite a lot about what the signals would look like if we were to have other measurements done here because we have, for example, the manufacturer's specifications as to what kinds of inputs this will react to and what that will look like on the output signal line. And that allows us as well to say something about what is happening inside the experiment. Now, data is clearly something much less than the signal. This signal here is something that we're going to summarize just by listing what the event time is. This is just an example of a much more general thing that a model is always much less than the world itself. Any map we create is always much less than a territory. And if you don't believe that, then you should go and read Borges on exactitude in science, which is rather a wonderful, just 1 or 2 paragraphs. So data, however much we have, is just a lossy compression of these noisy signals on these signal lines, but it does allow us to infer something about whatever there is in this region here or inside these devices, and so on. And indeed, we have centuries of experience saying something about things we know nothing about directly. So let's have a different prelude, this one data-centric. From the experiment we've just seen on the previous slide, we obtain these noisy data sets. They just contain lists of numbers. And from those lists of numbers, we can compute actual relative frequencies and other statistics for that data. Now, whatever theory we use, in any serious kind of way, should generate something that are expected relative frequencies that we can compare with the actual relative frequencies we're going to get out of future data sets. That will confirm or deny the theory in some degree. Anything more than that is not going to give us better empirical confirmation in any direct sense. Nonetheless, it can be useful to generate the expected relative frequencies in different ways, according to different theories. Each different theory will have different intuitions, different interpretations even as well. Intuition, which is a catch-all word, of course, could mean many different things to different people, but it says something about what happens between and beyond where we actually have data, where the data we're going to read between the lines of the data, something about what the data is saying that we would see if we had more devices thrown into the experiment, perhaps. Even though we don't have them there. So we can talk about the voltage in a very, very small region of space and time that we have not actually measured. And that gives us an overall intuition as to what's happening in the device. Metadata, later in the talk in particular, what we know about an experiment is something vital because it's only by knowing something about the experiment that we can decide how to interpolate between the data we have. Now, one example of an intuition is the idea of a system. Typically, people talk about particles and particle properties as well. And we talk about particles causing the outcomes that are recorded in the data sets that we have out of an experiment. But that relationship is rather less solid, should we say, than the relationship between the data sets and the actual measurements, where the signal becomes an item of data, which then is stored in computer memory in a relatively direct way. Particles and particle properties can be very helpful. They can give you an intuitive guide to what's happening in the experiment that can really work wonders when you start trying to do calculations about new experiments in particular. But they can also, of course, be misleading. And that's a large part of why we worry about the relationship between particles and their momenta, the positions of momenta, for example. So the thrust of this talk is that particle properties are not obvious enough to belong in a set of axioms, which they do because von Neumann established the axioms precisely to say this is a Hilbert space and this is the system that corresponds to that Hilbert space. Now, this is something that I think is quite strongly suggested by quantum field theory. It's certainly lukewarm about particles, and in the axiomatic forms, particles play no part whatsoever in the first construction of an axiomatic kind of a quantum field theory. There's also another reason, modern reason, for thinking in terms of data sets, and that is machine learning is really teaching us to focus on data sets without necessarily focusing on what causes the data sets, allowing the machine learning to do that deduction as to what causes the data sets without our necessarily too much of our input. Now, I'm not a great fan of the sort of adapting great authors to one's own purposes, but I'm going to regale you with one slide of such things where I'm going to reread these great authors. So Bohr in 1921 said, "In a certain respect, we are entitled, in the quantum theory, to see an attempt of a natural generalization of the classical theory of electromagnetism." And of course, 4 years later, all of that was going to be swept aside. Bohr in 1949 is saying something more subtle, of course. It's decisive to recognize that. However far the phenomena transcend the scope of classical physical explanation. So there you see, classical mechanics is not complete. It's not able to describe all the phenomena, according to Bohr in 1949, and indeed everyone else. But nonetheless, the account of all evidence must be expressed in classical terms. So we're going to start with classical description, but then we're going to find it's not adequate to describe all of the phenomena. But what I'm going to show you is how we can use the Poisson bracket to make non-commutativity, contextuality, interventions, and all that a natural part of in classical terms, and then the phenomena will not transcend that version of classical mechanics, that's CM+. Now, Dirac in the same year, 1949, is also saying, "My own opinion is that we ought to search for a way of making fundamental changes, not only in our present quantum mechanics, but actually in classical mechanics as well." Essentially, what I'm attempting to do here with CM+, it probably is not what he would anticipate doing, although the Poisson bracket was very much part of his thinking when he was thinking about classical mechanics. Bell in 1975 is saying something comparable, a little different, of course. Bell has very much his own mind. Observables must be made somehow out of beables. The theory of local beables, which I think, by which I'm going to take him to mean functions on a phase space or something very similar to that, should contain that theory of local beables and give precise physical meaning to the algebra of local observables, where observables, in other words, should be part of or deduced from, I'm going to interpret it as, the theory of local beables. So I'm going to use the Poisson bracket on the phase space to add new observables to give us CM+, and in some sense this is the opposite of adding hidden variables to quantum mechanics. We're going to add new observables into classical mechanics. Bell in 1990, in a rather famous article, Against Measurement, is quite stridently argues that we shouldn't talk about measuring things. And yet, on the last page of that article, he says, experiments have results. And I take that to mean that experiments give us data sets. And I hope to see how Bell, in fact, having worked 30 years at CERN, where the whole output is huge amounts of data in very large data sets, how he could possibly deny that there are data sets. There are results. And to continue with the theme of CERN, just this year, the CERN Courier in 2026 says, "The modern search program is increasingly motivated by signals rather than full theories." And of course, by signals, they are talking about an idealized form of data sets, and so on. Now, a very different theme, but also from this year, this is actually a politician, Glusenkamp Perez, who says spreadsheets can contain a part of truth, but never all of truth. Of course, this is just part of data is much less than the signal. There's more to be said that can't be said by data, but nonetheless, it is the game in physics is to play with the data, not to play with what we cannot say anything about. So now just this one slide, I'm going to suggest to you an elementary and concrete matrix model that is entirely classical, where for a data set, which I'm going to call M, that has data values in it, M1, M2, M3, and M2 again, and so on. For each of those data values, we have also a relative frequency between 0 and 1, which for actual data will be just a rational number, but for expected data, for expected relative frequencies, we'll allow ourselves to use real numbers because that's computationally more effective in many ways. So then the dataset average is just the sum of the products of those relative frequencies and those data values. So if we have the M1, for example, occurs as 20 of 1,000 entries, then of course its relative frequency, its probability, if you will, is 20 out of 1,000, 1 over 50. But I'm going to use a linear operator. I'm going to call this m hat, for which those data values, m1, m2, and so on, are its eigenvalues. So there is a basis in which the linear operator m hat can be presented as a diagonal matrix with the values m1, m2, and so on down the diagonal. Now, that doesn't tell us what the dataset average is. It just tells us what the data values are for any experiment that you might do for which you're going to use the m hat as a way to present that measurement, that type of measurement. But then to describe to give us the dataset averages, I'm going to introduce a thing called a state, which maps that m hat to a dataset average to exactly this number, and this number can precisely be written as the trace of these two matrices, where it doesn't matter what the values are off the diagonal, because those will all be zeroed out by the zeros in this particular basis. And so that these are relative frequencies, we require that this density operator should be positive and that its trace is 1, and that ensures these properties for these relative frequencies satisfy the rules that we require for a relative frequency. Now, if we have a different data set, m prime, and it also has a diagonal representation in a different basis, though. And because that's in a different basis, we have m prime in that different basis, the diagonal entries for rho hat in that different basis are different. And so we have a sum of a different set of probabilities, relative frequencies, pi prime with the mi prime, even though we are using exactly the same rho and rho hat. And these pi primes also satisfy the rules for them to be relative frequencies as well. So what we've done here is we've encoded into a single formal structure many different probability spaces, obviously more than two are possible. There's no physics in this construction. This is just mathematics. There's no h-bar. There's no complex structure either. This is just a matrix model of what the mathematicians now call a generalized probability theory. And even 30 years ago, very typically, this would be called a quantum probability theory. But it's not. It's perfectly good mathematics. It's just matrix algebras. And it encodes very nicely something that can usefully be encoded together. Now, you can even find an early intimation of this particular mathematics in George Boole's book in 1854, The Laws of Thought, where he essentially presents something very similar to the Bell inequalities. You can find this presented to the philosophy literature, for example, in Itamar Potowski's article in the British Journal of Philosophy of Science in 1994. You can find the account that I've just given here at a mathematically much higher level, indeed in terms of category theory and so on, in an article in the New Journal of Physics in 2011. So for traditional classical physics, we use different initial conditions for different contexts, should we say. You take one initial condition and you evolve it with the differential equation, say, to later times. On the other hand, we can also take different initial conditions and evolve it with the same differential equation to later times as well. What operator algebras allow us to do, is it gives us more tools. For modeling incompatible experiments, multiple initial conditions can be encoded in the same structure, and then we can encode them all at once, should we say. Now, that requires more work to set up the initial conditions for this extra information. It has to be found and encoded correctly, but that's something we know very well from quantum mechanics is useful to do. And there's no reason to think that it shouldn't be useful also for classical physics. From an engineering perspective, at least. Now, I just want to focus for a moment on how we can think about data analysis and data sets and relative frequencies relative to the mathematics we usually use in quantum mechanics. From a data analysis perspective, so for a data set, just a long list of numbers, not thinking about an ensemble of systems and their properties at all. A relative frequency is just an integer ratio between 0 and 1 in a particular context, C as I'm calling it here. We're allowed to add relative frequencies in the same context. So long as there's no double counting, we obtain a new relative frequency. And even more than that, if we add relative frequencies with no double counting and no emissions as well, we'll obtain the number 1. So there's that normalization. Now, we have to keep track of double counting, and one way to do that, the commonest way, is to use sample spaces and sigma algebras, but really all that's important is we keep track of make sure we don't double count. And when we want to not omit anything, make sure we don't omit anything. Historically, the Kolmogorov axioms of probability followed that mathematics of relative frequencies. If it had not been so, we would be talking about someone else's axioms as well as Kolmogorov's axioms. Relative frequencies are too manifestly a use case for probability for there to be any real difference between these. And indeed, we can think of relative frequencies as giving us a model of the Kolmogorov axioms over the rational numbers. In contrast, expected relative frequencies, what are also called probabilities, give us a model of the Kolmogorov axioms over the real numbers instead of over the rationals. And we can also talk about formal Bayesian beliefs and things like Dutch book arguments that say that Bayesian beliefs ought to follow the logic, the mathematics of relative frequencies or probabilities. Otherwise, you'd be able to beat me at whatever game it is we're playing. That also gives us a model of the Kolmogorov axioms over the real numbers. And we've seen on the previous slide how we can use algebraic models of the Kolmogorov axioms over the real numbers as well, and indeed encode multiple probability spaces into one structure. Now, I want to emphasize this is not an interpretation of probability in terms of relative frequencies. All it is it's an assertion that relative frequencies are models of the same mathematical rules. Relative frequencies and probabilities satisfy the same rules. We can add them so long as we don't double count. And we can add them with no double counting and no omissions and get 1. Those are rules that are satisfied by probability as expected relative frequencies, just as they are by actual relative frequencies. Now, we can look at von Mises' axioms, for example, as one way to try to unify actual and expected relative frequencies. But to do that, von Mises introduces infinite data sets, and which is unrealistic, shall we say. What actually happens with real data is that sometimes you get one piece of data will change a whole theory. Another time, many gigabytes of data will have no effect on theory. We'll say, well, we're going to wait for more data before we change our theory. There's reasons to believe that this is not quite such good data for some reason. The whole story gets quite wild in some cases. Decision theory, which is the game we play to decide what to do with some new data, is really quite a wild west. What we saw on the previous slide, generalized probability, what that does, I suggest, is it gives us ways to interpolate between different contexts. So we have a lot of information from many different experiments, that in the first instance will tell us nothing about a brand new experiment. But we want to use all that information as well as we can to predict the results for a new experiment, for new initial conditions, even though they are completely different to the experiment we've just done. So long as we can place that new context relative to the earlier context, we can infer expected values for those new relative frequencies as well as perhaps is possible, given that the placement we've chosen is well chosen. Generalized probability theory, in other words, just gives us more tools for deciding what to do with new data and with old data and how to mix and match them. So how do we apply this kind of thinking to the two-slit experiment, where we're talking about data more than we're talking about anything else? We used a number of devices, just as we had in the schematic a few slides ago, and each of those is connected by a signal line to a piece of hardware that analyzes that signal in real time, and, for example, counts the number of times at which, or when there is an event that happens on each signal line per second, perhaps. Even when we can insert those devices into a dark room, there will still be some events will happen, nonetheless very few. For each of these devices, for D1, we'll have a measurement operator, M1, and so on. Different for each measurement device, but we'll use the same state to tell us what the expected or actual relative frequencies are for the particular values that you can obtain with the measurement M1, which will just be a list of 0, 1, 2, 3, 4, 5, up to however many can possibly occur in the 1 second interval. In the dark rate case, even in the dark rate, the power line might perhaps have a certain amount of noise on it, and that will have some effect on what the dark rate is. Now we change the room that we're working in. We introduce a light source, and so the surroundings for each of these devices changes. And because the surroundings have changed, there will be a change. And we can record that change by having a different state, but acting on the same measurement operators, because after all, the sample space for those measurements is going to be exactly the same. We're going to have 0, 1, 2, 3, 4, 5, etc. For all those, the M1 does not have to change. So the statistics of the events in each device will change, not just the average numbers, but also when we construct statistics, the statistics will be different in really quite complicated ways, perhaps. Now we introduce a double slit. So the numbers change again, and so we have a different state, row 2. We change the width of the slits, and so we have a different state, row 3. We move the double slit, we have a different state, row 4. We can describe all this using this mathematics really quite straightforwardly, even if we have no real understanding of why the numbers change. So there don't have to be any particles causing the events in our devices in the first instance. Later, we'll perhaps be able to say something about, well, what the particles are doing, but sometimes, indeed, in the double slit case, it's quite hard to say what it is that particles are doing from here to here, but we can still describe the numbers of events. So we're going to call whatever there is between the source and measurement, well, we can call it the whatever there is. We can call it the surroundings. We can call it the vacuum. We can call it, really, the name we give it does not matter. There is something happening in here, I'm quite happy to say. And indeed, I'm happy to say, after this talk, but not during this talk, that there are particles causing those events, if you like. We can go back to thinking about particles and particle properties. We're just going to back away from that for the purpose of this talk. So I find it a little interesting to just consider what these avalanche photodiodes in particular might be. Any device, you have a device and a signal line to something. That avalanche photodiode is absolutely not a straightforward piece of apparatus. It's taken us a century, 2 centuries arguably, to get to the point where we have increasingly sophisticated, every decade sees improvements. It requires remarkable materials and remarkable processing. This is, it's just not ordinary clay. The avalanche photodiode mostly just burbles along with its surroundings, but then sometimes the signal goes to a higher level, and that's just something more interesting than using devices that do nothing. You could use a device that just had noise, but that would be much more difficult to analyze in some sense than a device which is designed to give you events that can be recorded. Once the event has happened, then the APD's electronics has to calm it down as fast as possible. This time is a time when you can't record another event, and so we try to make that as fast as possible, so it can burble again, so that we can get another event. Now, an avalanche photodiode does actually tell a story, even when it's only burbling. And indeed, Zlatko Minev, in an experiment at Yale, as part of his PhD thesis, and recorded in a Nature article in 2019, looked at the signal here and was able to tell whether or not an event was about to happen, and was able to tell the electronics was able to change the electronics so that the event didn't happen. So then, of course, he does record that an event would have happened had he not stopped it from happening here. So this is a different kind of event, so to speak. It's not actually abolishing events, it's just giving us a different kind of event, which analyzes the signal here to decide whether an event would have happened if we hadn't changed things. I find it's also interesting to consider the frequency scales involved in just an ordinary avalanche photodiode. We have the optical scale is about 10 to the 15 cycles per second. The electronic scale, where this signal is changing, might be at the gigahertz scale, or comparable to that at least. Then we have the thermodynamic scale of when events happen, and that typically would be at something like megahertz, perhaps 10 microseconds between them. Then we have the human scale, my heartbeat, perhaps also how fast I think or don't think. Then we have as well the experimental scale, between of the order of 10 or a dozen days to 30 years for the case of nanohertz. Because if new experiments come along, they come along only infrequently, but nonetheless they keep coming. There is, so to speak, a cycle of different experiments, and the avalanche photodiode fits into those in some sort of way, and of course also improvements into the avalanche photodiodes over time as well. So we have these noisy devices, avalanche photodiodes or otherwise, and they are put into noisy surroundings, resulting in noisy signals, and we analyze those signals and decide what events there are, and we record that as data, and perhaps those events are caused by particles. But this is quite a fraught moment. How do you decide which events go with which particle? Early on in the data, you might see that there are these 5 events, and you say, oh, well, clearly those are all associated with one particle. They're in a nice straight line. A little later, though, these 2 extra events are also reported, and we notice that this event here might be caused by this particle that we've also decided here. So is this event caused by this particle, or is it only there because of the 2 particles being there at the same time? There's no way to tell from just this bare data. There's another aspect to this, and that is that these events to particles algorithms are going to be global. It's only after we've got all the data in for the whole experiment that, in a way, we can decide how the individual events will be assigned to particles. Now, that just means that these algorithms are relatively fragile. You have to be careful with them. They are subtle. They shouldn't be in the axioms. Yes, there can be particles, but we've got to be careful. So I should also admit that the idea of converting a signal into events is also a little bit fragile, because we could record the time of the event here, but we could also record the event of the time at the event timers in the middle of this elevated voltage, or slightly before or after, or as with Zatko-Binev, perhaps here, because we could tell from the signal here that an event was about to happen here. So also fragile. Nonetheless, there's a sense in which I think this is less fragile or differently fragile. It's also differently non-local than the events to particles algorithms. This is something that we might or might not want to rethink in future. For my purposes here, I'm not going to rethink it much. It's also worth, I think, mentioning that when we measure signal levels, we can do so on a schedule of every nanosecond, say, or every picosecond if we can do it that fast. But these events don't happen when we want them to. They happen when the device thinks to itself, oh, I will do it. Whatever it is that it does, that's what the event will happen to, its own schedule. So now we'll dive into how we might present this in algebraic way, hence differently from the usual ways you'll see quantum mechanics presented. This is something you can find in the literature. There's even a textbook that describes algebraic quantum mechanics quite well, and at a relatively elementary undergraduate level. But then you can also find a dictionary article by Klaus Landsman, which is rather beautifully succinct. And there's also a rather nice, longer discussion in this recent preprint. The principle here is to take von Neumann's idea that a Hilbert space should correspond to a system, which is his first axiom and is the axiom you'll typically see in modern textbooks, and replace that by the idea that the eigenvalues of a linear operator, the diagonal entries in a matrix, in a particular basis, will correspond to the data values in a particular data set. A much more direct relationship than this rather unclear statement about how quantum mechanics is to work. So we're going to say there are abstract measurements, M1, M2, M3, we can add them, we can multiply them, where indeed a data set's data values correspond to a linear operator's eigenvalues And if we were thinking classically, it would correspond to a random variables sample space. Same language, different language, but for the same idea. If the algebra is non-commutative, we'd call it quantum. If the algebra is commutative, then we would call it classical. And I also assume these four properties because I do want to make contact with quantum mechanics. And so, as we did for the elementary matrix example, we introduce a state that will tell us expected data set averages when we collect data, or if we collect data, for these measurements which don't tell us what the expected data set averages will be. It only tells us what the data values will be. And so we have the state applied to M1 will give us an expected value for it. But we can also, with a very straightforward algebraic expression, introduce the nth power of that measurement operator, and that will give us the nth moment of the same data set, for the same data set, and similarly for M2 and so on, and for the addition and multiplication. Now, these moments of the data set we're going to be using so extensively that it's extremely useful to have a generating operator for those moment generating operators. So we'll have a generating operator for those moment operators, which will just be the exponential. And I'm going to introduce an imaginary, which I'm going to call J, because the purpose of this is to take the inverse Fourier transform of this to produce a probability distribution. So this, in many ways, mirrors the use of the engineer's imaginary for Fourier transform in signal analysis. So this generating operator, when we apply a state to it, gives us a characteristic function, which is just the Fourier transform of a probability distribution. So this is how we will write the probability distribution for a particular measurement in a particular state and at a particular value. And that will all work quite well in an engineering kind of way. For the mathematicians, will want to present this rather more precisely in terms of projection value measures and so on. Now, a state in the literature satisfies an absolutely routine set of conditions which are entirely intended to match the kinds of rules we have for relative frequencies, because these are indeed intended to give us probabilities. At least now, when we first started, of course, in 1925, we initially had no idea these were going to be probabilities. But by now, we know we want to work towards probabilities. Relative frequencies have four properties that we're going to require also for a state. Relative frequencies are positive, they're normalized and real valued, and correspondingly, we have these three algebraic statements which do exactly that. And because we can add relative frequencies with the usual rules, we have von Neumann linearity, by which I just mean that even if A and B do not commute, nonetheless, this equation must be satisfied. And we need this, for those who know what a positive operator value measure is, those will only work if we have von Neumann linearity. It's not enough just to have linearity only when A and B commute. Now, another aspect of why defining a state this way is so useful is because this construction, where we take any operator A and its adjoint and bracket it around a measurement operator and normalize it, this satisfies the rules for it to be a state. These four rules are satisfied by this construction too. So that gives us many states, which I'm going to call modulations of the initial state rho, because I want to use signal analysis language. This gives us different expected measurement results in a different state. And this is the basis of what's called the Gelfand-Naimark-Siegel construction of a Hilbert space. So where up here we said we're not going to talk about Hilbert spaces, down here we have managed to construct Hilbert spaces and all the mathematics of operators acting upon them. This is going to be just the same mathematics as we're used to in quantum mechanics, but we're talking about data sets instead of about properties of particles. Now, GNS construction, as it's called, lets us also think of a state applied to a measurement operator as a vector and its covector bracketed around a measurement operator, and similarly for a modulated state. Now, all this is very old. It dates from 1931 in the case of Koopman, where he suggested using Hilbert spaces for a classical mechanics formalism. That was used almost immediately by Birkhoff and von Neumann to prove versions of the ergodic theorem, and then drops off the face of the planet. There's almost nothing in the literature until Sudarshan in Pramana 1976 says, hey guys, this might actually be useful for classical mechanics, particularly for chaotic systems. And that has become a whole industry in dynamical systems of what I call Koopman methods. There's a really nice 100-page review of how that's used, particularly for machine learning, for example, as well, in Science Review 2022. There's a history, a very nice, very recent history by Jacob Barandes of Koopman's methods up to around about 2000. Now, there's also in the literature, in 1926, in June 1926, Carl Eckart has this really nice title, Operator Calculus and the Solution of the Equations of Quantum Dynamics. It turns out that he didn't know about Schrödinger, who just very shortly before him had introduced his Schrödinger's approach to quantum mechanics. But the first section of his paper is all about operator calculus in a way that is very reminiscent of the way in which I'm going to show you on the next slide. We can think about classical mechanics and the Poisson bracket. So now we have three ways to compare quantum mechanics and classical mechanics in the same formalism. We have Wigner functions and the Moyle brackets, for example. There's a large literature on that. I think that has not quite fulfilled its promise as a way to understand quantum mechanics relative to classical mechanics, partly because of the additional structure that's involved in working with functions. Whereas with Koopman's Hilbert space approach, there's slightly less things getting in the way of understanding. And if we think algebraically, as Eckart suggests we might do, and so I think of this as Eckart's formalism, should we say, this gives us a third way to discuss the relationships between quantum mechanics and classical mechanics that can turn out rather differently from quantization. So what does algebraic classical mechanics look like? Now, I described this in an article in Annals of Physics 2020. It's common to take classical mechanics to be an algebra of functions on phase space. So functions of position and momentum in the simplest cases. It has three binary operations. There's addition and multiplication. Now that's a commutative algebra, but it also has the Poisson bracket as also a binary operation. So this is not a commutative algebra. So we have u plus v, u times v, and the Poisson bracket, which is even not associative. This is not an elementary algebra as we used to in high school, for example. But we can construct a simpler transformation algebra that is exactly the same kind of structure as we used to in quantum mechanics with only addition and composition by introducing two unary operations, as they're called, because they act on a single object. We have multiplication by w, just use the multiplication operator to multiply by w. And then we can use the Poisson bracket in exactly the same way to construct what I call Poisson by W, Z subscript W. We can then use the Jacobi identity in just a very few lines to demonstrate that this is the set of non-trivial commutation relations that hold between those Y and Z operators. Now, just to give you a small idea as to what this kind of thing is doing, we have Poisson by W just gives us a generator of W transformations. It gives us a way to move points in phase space around, so to speak. Where a familiar example is Poisson by the Hamiltonian function. That gives us a generator of time evolution. It tells you what the trajectory in phase space will be for the particular Hamiltonian. And that's something we call the Liouvillean operator. What I've been suggesting is that we can use these Z's as well as the Y's to give ourselves something more powerful than classical mechanics, so I call it Cm+, so long as we're willing to use those Z operators without any restriction, by which I mean that we allow ourselves to use the nth power of those and not just using them as generators of W transformations, for example. If we're willing to do that, and I'll show you why we haven't been willing to do that in a few slides' time, that gives us an algebraic measurement theory that is shared with quantum mechanics. It's something that includes non-commutativity, it includes measurement incompatibility, and there are all sorts of other ways of thinking about this, all of which become classically very natural once we start thinking in terms of the elementary matrix model that I suggested on slide number 7. Now, the payoff for this is that we can have isomorphisms between CM plus and quantum mechanics. And that's instead of the usual relationship of quantization between ordinary classical mechanics and quantum mechanics, which is not an isomorphism, and as a consequence, the reverse process of going from the quantum mechanics to classical mechanics has to be a rather ad hoc sort of set of rules, one of which is the correspondence principle, for example. So it's in some ways better to have isomorphisms. On the other hand, this definitely doesn't replace quantization, the correspondence principle. This is just a different way of approaching the relationship between them. We can use both according to the circumstances. So now that previous slide was really quite general. It applies for any phase space, even if it has a very complicated topology, like a donut or some such. So I'm going to show you for this classical simple harmonic oscillator what this looks like, but also because constructing a state for something more complicated would be much more complicated as well. So for the simple harmonic oscillator, we have the Poisson bracket is just this expression here, a derivative applied to both V and U, and antisymmetrically because we take the P and the Q derivatives in the opposite order. So we have, for the multiplication by Q is straightforward and multiplication by P is straightforward. Poisson by P just becomes a derivative with respect to Q. Poisson by Q becomes derivative with respect to P with a different sign. That gives us two copies of what are called the Weyl algebra, for which this commutation relation is satisfied. Now, for the Hamiltonian function, we have multiplication by that is this positive operator. For the Poisson by the Hamiltonian operator, however, this is not a positive operator, and we will talk about the consequences of that in a few slides' time. Now, for a statistical state over this algebra, the natural place to go in the late 19th century is the Gibbs thermal state. For a simple harmonic oscillator, which we know at temperature kT is just a normal probability distribution. So we saw earlier that the way to write down in this formalism a probability distribution in the Gibbs state is just to use the Dirac delta function with the operator yq and yp. And because these two operators commute, everything works out nicely, even despite this being a more elaborate sort of construction. And we can write down on the right-hand side the normal probability distribution with the variance given by kt. The amplitude of the noise, the thermal noise, is given by kt. Then we can take the Fourier transform of that probability distribution, which gives us this expression, the characteristic function for that. And again, I'm going to use the engineer's imaginary J, just because this is all about using the Fourier transform. Because we've introduced the engineer's imaginary J, you may perhaps not want to join me in this, but for the purpose of this talk, and indeed I feel this is adequate for my purposes, this is now the Weyl-Heisenberg algebra because we've introduced an imaginary. So we can use raising and lowering operators. So we have that the multiplied by Q we can write as the sum of raising and lowering operators. For Poisson by P we can write as the difference of raising and lowering operators, and setting the usual commutation relation for those, we obtain the commutation relation we require that we have up here, and we set the action of the lowering operator on a thermal vector to be 0, as we do in quantum mechanics. And similarly for yp and zq for a different operator b, acting also on the same vector to annihilate it. So now, with that construction, we can compute, using the Baker-Campbell-Hausdorff identities, what the expression we should expect for a measurement of the Poisson of these Poisson by Q and Poisson by P operators, and it is also just a Gaussian expression. Now, because we've introduced this thermal vector and these raising and lowering operators acting on it, we can construct modulated non-equilibrium states. And that will give us, with the GNS construction, a thermal Hilbert space. So now this is entirely classical. It's all about temperature, not about quantum noise. So instead of trying to map classical QMP to quantum QMP, which quantization tries to, we can instead map Q and J partially Q to Q1 and P1, and that is an isomorphism, and so is this. It's an isomorphism. It's not a unitary equivalence because kt is not equal to h bar, and indeed kt is not even the same units as h bar. Thermal noise is not quantum noise. It can't be the same sort of thing because if it were the same sort of thing, the whole history of physics in the 20th century would have been different. But as for quantum noise, this Gibbs state is also about something that's really completely unknown and irreducible in some sort of way, because we don't know anything about what the heat bath is. We don't know anything about the interactions. We only know that the heat bath and the interactions together act on the simple harmonic oscillator to give us the effects that are well described by a Gibbs thermal state of this form. So this is just as confusing in a way as quantum noise, or unconfusing, depending on your point of view. So what is the difference between quantum and thermal noise? We have different units of action. H bar is units of action, whereas KT has units of energy. That doesn't give us a clue as to what to do next, however. What does give us a good clue is if we look in quantum field theory, where we find that the quantum vacuum, which is where quantum noise lives, so to speak, that is Lorentz invariant, whereas thermal noise is not invariant under Lorentz boosts. And indeed, one can calculate for the two-point function in the vacuum state and the two-point function in a thermal state for the real Klein-Gordon quantum field theory, that there are differences between those because they are different, one of which is Lorentz invariant for just the vacuum state. The other, though, is exactly the same except for this extra factor, the hyperbolic cotangent, with K0 here, so this is not invariant under Lorentz boosts. Now this is a difference of symmetry properties that can be perfectly well used in CM+, where we take h bar to be an amplitude of a Lorentz invariant noise, and kt can be taken as the amplitude of a less invariant thermal noise. And when we come to much later in the talk, I'll show you how that looks in some more detail. We also should point out that quantum and thermal noise, we know, are closely related by the Unruh effect, and just by changing the coordinates to an accelerated system of reference, we can change what looks like quantum noise into what looks like quantum and thermal noise. They really are of the same kind, but slightly different because of their symmetry properties, which is really strikingly shown by the Unruh effect, I think. Now, what I think this demonstrates, however, is that we must work with field theories. We've introduced the difference between these different kinds of noise as a matter of geometry. And we can only define the Lorentz group in at least 1 + 1 dimensions, and we want to work in 1 + 3 dimensions for much of the time. Two rather random sort of ideas that I think have to be pointed out here are that for CM+, the limit of h bar approaches 0 is no longer a classical approximation. It is an approximation we'll want to use whenever possible because that will give us a simpler mathematics, but CM+ in itself is perfectly happy with h bar being non-zero. Also, we have to point out that entropy is associated with KT. It's not associated with h bar. And in the journal, ironically, perhaps, titled Entropy in 2014, you can find an article with the title Quantropy, which indeed might perhaps be the name we will give to the thermodynamic dual to Planck's constant. So CM+, I've argued, can and should include non-commutative quantum noise. It gives us a quantum measurement theory that's just the same as we have for quantum mechanics. CM+ is just Hilbert spaces. It's just what Koopman suggested, but we've added in non-commutativity, which Koopman did not do. But there is a much more important technical difference, and that is that for quantum mechanics, the Hamiltonian operator is bounded below. And that's a consequence of the correspondence principle, which says that the frequency corresponds to energy. And the consequence of that is the positivity of the Hamiltonian operator, and the consequence of that is a whole set of analytic properties that are very important in how we use quantum mechanics. It's not something that any mathematician is going to want to give up. But for CM+, that is not the case. If we look at multiplication by the Hamiltonian operator, Hamiltonian function, that indeed is greater than or equal to 0. It's a positive operator. But for JZH, the Hermitian generator of evolution, it is not a positive operator. And as a consequence, CM plus does not have those analytic properties that are so desirable and so useful in quantum mechanics. Now, we could change CM plus so that it also is it just looks exactly the same as quantum mechanics, but it's enough to have the same measurement theory. It's useful to have two different kinds of models, the CM plus kind of model and the quantum mechanics kind of model, so we can compare and contrast the two. Analyticity is mathematically useful, but we don't have to have it. But what we can do is adopt from signal analysis a kind of naming for this, and that is we can say that quantum mechanics is an analytic form of CM+. And this corresponds very much to the ways in which we talk about the analytic signal in signal analysis, where only positive frequency components, there are only positive frequency components, or we can talk about the real signal, which does have both positive and negative frequency components because we add them together to get the cosine. So why has this mathematics not been used for decades? Classical mechanics has been, as the philosophers would say, straw-manned. We've tied its hands behind its back and told it to fight it out with quantum mechanics, and it loses every time. For a classical simple harmonic oscillator, we are allowed to use partial Q to generate translations. So we have this adjoint action of ZP exponentiated acts to generate a subtraction of a constant from the multiplication operator. And that is something that seems perfectly reasonable. But we're not allowed to use ZP cubed by convention to generate a similar unitary transformation, the same kind of adjoint action, same kind of raising of ZP cubed, but into an exponential, because that results in adding to the multiplication by q partially 2 by partially q squared. So that's something very different. Except, of course, it's not very different from the perspective of quantum mechanics, where we happily use ZP cubed to transform to a different experiment, to a different experimental context. That can be useful in just the same way for classical mechanics. And indeed, this is just to do what I showed you in the elementary matrix model on slide number 7. If we unlock that superpower for classical mechanics, we can steel man classical mechanics, CM+. The idea of what an initial condition, however, becomes more complicated because we have many of what we would call classical mechanics initial conditions all encoded into a single structure. We have to know more in order to say we've got the initial condition for CM+ set. We might, if we didn't have the example of quantum mechanics, say, oh, that's no good. But in practice, this is something that's extremely useful. Quantum mechanics is powerful because we have to do the extra work. We have to do quantum state tomography, as it's called, to establish what the state is by doing lots of experiments in order to determine the initial condition for CM+, for quantum mechanics, instead of the much simpler establishment of what the initial conditions are for classical mechanics. Now, we've added into CM+ non-commutativity. That has the consequence of having the same measurement theory, and consequently has the same measurement problem as quantum mechanics. And I found this to be very helpful for rethinking how we should approach quantum mechanics problem, the measurement problem for quantum mechanics. I'm going to discuss it as if there's only quantum mechanics, but just keep in the back of your mind that CM+ does have this same problem. And it looks exactly the same because of the isomorphisms we can construct between them. So if we have two measurements, A and B, that have different data values for the two, then we can write the measurement operators that correspond to those measurements as a weighted sum of orthogonal projection operators, and in a particular basis, that will be a set of that set of data values down the diagonal of a matrix. If we have a measurement of A, where we have a state vector psi, then the way we compute the probability for that result alpha m is just by taking the vector psi and its covector, bracketing it around the projection operator, and that is effectively just the Born rule, at least for simple cases where we have just the projection operator is just a shorthand for this operator, and that gives us this expression, which is just this, which is very clearly the Born rule. But if we take two measurements, where we're going to do A first and then we're going to do B, Before we do the B measurement, what we say is that the result alpha m collapses the state vector. So psi becomes psi m, where we use the same projection operator acting on the vector psi, and we normalize it so that the probabilities work out right. And this is what's called the Löder's rule, known since the 1930s. Then we measure B in that new state. So we obtain the result alpha n followed by beta n, and this now is a conditional probability. The probability that we get beta n, given that we already had alpha m, is just constructed using the projection operators for the B measurement in the new state. That gives us this expression, multiplying it all out. And so the joint probability, the probability we got alpha m and we got beta n, is just given by this expression. Keep that in mind. For the top of this next slide, we have that the probability is given by this operator bracketed between psi and its covector. So these positive operators generate these joint probabilities for the results alpha m beta n. Now we can flip the script, so to speak. Instead of thinking of collapse affecting a state, so psi becomes psi m on the previous slide, we can instead take collapse to affect the next measurement. Qn, the next measurement's projection operator, becomes this more complicated positive operator, and that allows us to construct a positive operator valued measure, as it's called, a collapse product of A collapse B with the data values alpha m beta n, and we can do that even if A and B do not commute. Now this is something that in fact is very close to what Bohr would say about measurements, because instead of Heisenberg and von Neumann, for example, saying, oh, the state collapses, Bohr would mostly, and in fact really didn't want to talk about collapse at all. Instead he would say measurements affect other measurements. They affect the possibility of doing other measurements. So you can't do the measurement Qn after you've done the measurement A. You have to do the measurement that's described by this projection operator instead. So this is, in many ways, a mathematization of what Bohr said for decades. And very elementary, of course. You can find this in the literature. I'll show you. There are some links on a subsequent slide. Now, the existence of this joint probability is something we would traditionally say is rather classical. And indeed, the mathematics works out perfectly straightforwardly. We can introduce two commuting operators, A prime and B prime, and we can introduce a different vector state psi prime and a different Hilbert space H prime. So change everything. Because all we want is a matrix, the Mn matrix, that just gives us the same values as this matrix for the different values M and N. And we can do that perfectly well because we're not limiting ourselves to a small Hilbert space here. We can use a much bigger Hilbert space if necessary. Now that looks rather ad hoc, but mathematically this is something that has its own theorem, the Naimark dilation theorem, which constructs a joint measurement, AB, in a larger Hilbert space, just as I have done in the lines above, that is the same as this positive operator valued measure, the A collapse B, and this can indeed be an alternative to decoherence. So what's decoherence? In these sort of terms, decoherence takes a large Hilbert space, a huge Hilbert space model, for whatever's measured, whatever's measuring it as well, and everything else in the whole universe, and shows that the environmental noise from that whole universe will very nearly collapse the state for whatever's measured to an after measurement state. And that works very nicely, of course. We've been using that very happily for 50 years at least. Naimark, however, is somewhat the opposite. It takes a small Hilbert space for the coin we're tossing, for example, constructs a joint probability when we measure it twice. For consecutive measurement operators, that gives us a model for joint measurement outcomes in a larger Hilbert space, because the first measurement affects the later measurement. So we're describing measurements in the context of earlier and subsequent measurement outcomes. So Naimark is doing something which we're well used to doing. We start with a small model in classical physics and we build it out into larger and larger models. If we start by just recording heads or tails for the coin we've tossed, nonetheless, at some later time, we may say, well, we want better predictions. So we'll take a video of the coin, and halfway through the flight, we'll know much better whether or not the coin is going to land head or tails. And indeed, we're doing that kind of thing routinely now with many different dynamical systems, even quite chaotic dynamical systems. We refine our model to make it more complex, to make it a larger Hilbert space in the particular case we're discussing here. So we can use linear coherence perfectly happily, but we can also use NIMARC. Whichever seems easier for a particular experiment, we use whichever seems more appropriate. Now, that is just for 2 measurements I've just described. Once we go to 3 or more measurements, where we must do that because we don't just do 2 measurements at time-like separation, we do multiple, 3, 4, and indeed thousands. We can use the mathematics of what's called the sequential product. Or indeed, there are more elaborate systematic constructions, but this is the simplest one that actually does what we need. This takes 2 positive operators, x and y, and constructs a new positive operator. This is also positive, and so it can also be used as a projection operator, as a way to construct positive operators, to construct probabilities, excuse me. So now we have collapse of the quantum state after measurement can be written in 2 different ways. We can say, well, A collapses the measurement, collapses the state to a different state, which then we measure B in, and then we collapse to the appropriate things for that new measurement. And then we do a collapse for, then we measure C in that new state. Alternatively, we can do what we always do, which is to just say we'll collapse there after A, but then we'll do B collapse C, so the different bracketing, and with that different bracketing, we get this much simpler without a square root sort of thing. Nonetheless, this construction, this is non-associative. So there's something more complicated than the Heisenberg cut ambiguity going on here. There's what I'm going to call the bracketing ambiguity. Of course, we have a convention which says no square roots, thank you. And most of the time that's perfectly okay. However, if you look in the measurement theory literature, you will find this kind of construction where we take A collapse B followed by collapse C, because that sometimes is a more natural pairing for a particular apparatus, particular experiment. Nonetheless, we'll try to adopt the no square roots convention wherever possible. Now, there's a place where this really comes to a head, and that is for signal analysis, where there may be hundreds of millions of measurements at time-like separation even. We can use non-commuting operators as we usually would in quantum mechanics. So we would take an initial state rho, apply the measurement, do a collapse. Apply a different measurement, apply a different measurement, apply a collapse, measurement, collapse, measurement, collapse, all the way to the end here. The aim of which is to construct a joint expected relative frequency for the measurement results U1, U2, U3, UN, which is indeed a measurable thing, something you can measure. And since it's something you can measure, you must be able to predict what the measurement results will be with a suitable algorithm, which indeed quantum mechanics has. It's called the collapse of the quantum state. But we can instead use an essentially classical sort of approach, where we take a different initial state and never have to apply any collapses because all of these measurement operators commute. But nonetheless, there is plenty of capability to represent this same expected relative frequency. There is a difference here that the Hamiltonian evolution is a positive operator, which is something that's useful to have, even if you have to pay the price of collapse. Whereas for the Liouvillean evolution, we have the Liouvillean operator, or indeed its emission equivalent, is not a positive operator. So what I'm saying here is that collapse can be a dynamical process if you like, but we can also take it to be an algorithm for constructing joint probabilities. This is not something that is completely unique to me. It's not easy to find things in the literature that are comparable to this. Lalloe in 2019, or indeed actually the first edition of that book is 2010, I think, does have a section in which he talks about getting rid of state vector reduction, which is very comparable to what I've suggested here, but not as much developed. We also have Vetrick describes something rather similar too, and you can look up the principle of deferred measurement, which looks very similar to what I'm doing here. Again, however, the wider consequences of that, I think, are not developed as much as I'm going to show you here. So we have a necessary trade-off here. Quantum mechanics is effective when we need to use incompatible measurements, which we often do. But if we want to do joint measurements, then we're going to have to use collapse. On the other hand, CM Plus is very happy when we're just doing joint measurements, but it really needs a lot of work. You have to use the Poisson bracket in rather smarter sort of ways in order to model incompatible measurements. So depending on the experiment and the set of experiments we want to model, we'll use one or the other. So I find this quite a helpful way to think about it. It's a little disconnected from what I've just shown you, but the Schrödinger picture famously applies both unitary evolution and collapse to the state. The Heisenberg picture, on the other hand, applies collapse to the state, but applies the unitary evolution to measurements. What I'm going to call the super-Heisenberg picture applies unitary evolution and collapse to measurements. Now, this is not a unitary equivalence, so it's not the same as the relationship between the Schrödinger and Heisenberg pictures, which is a unitary equivalence, but it is an empirical equivalence because, as we've just seen, we can model the same expected joint statistics. Now, I find this kind of satisfying as a unification of sorts, because if we focus on the classicality here, we could call this the Bohr picture. And indeed, for Bohr, measurements affect other measurements. They don't affect the state. This is something that Don Howard in 2004 really describes very effectively. But we could also focus on the commutativity aspect of this and say, oh, this is quantum non-demolition picture of the experiment, or this is a consistent histories picture of the experiment, which also, that's an interpretation which also depends on commutativity at some level. But because it's no collapse, we could also call it the Everett picture, perhaps. Although for this, we can have branching if we like, but we can also work with it as if it's just mathematics, in which case the branching aspect, that ontological claim of branching, is just not necessary. And of course, there are other no collapse interpretations of quantum mechanics, not just the Everett interpretation. And also, because it's rather classical, we might even call it the Einstein picture. Einstein might object that, no, God does not play dice, in which case he would dismiss this, but because, of course, this does have a Poincare invariant noise. Now, something to point out is that there is a literature, a classical literature called causal modeling, which discusses interventions, which addresses this running joke that correlations are much less than causality. You can't deduce causality just from correlations, you need more. And they introduce a formalism in which we can talk about, do x equals x, the experimenter decides that and enforces, makes sure that the random variable x will have the value x. And that's very different from, in ontological terms at least, from saying, from discussing conditional probabilities of y given that x happened to be x. So this is a way to discuss counterfactuals. This introduces tools on top of the ordinary tools of classical mechanics, the ordinary tools of classical probability. So in that sense, this is very similar to CM+. And indeed, collapse and the projection operators can model this idea of intervention, or perhaps what we might call state preparation, in a classically natural way. So we can talk about the projection operator for y equals y, which is the way we talk about the probability for the random variable equaling y, together with a projection to a subspace of the whole Hilbert space for that value x applied to the density operator we first thought of. This is a way of making connection between a different kind of approach to the problems that we're trying to address with quantum mechanics, but in a classical framework. So now to start thinking about classical fields even more than we did when we talked about the twin-slit experiment. When we think carefully about noisy classical fields, whether I am alive or dead is something that's quite complicated. Just because I'm lying on the floor does not mean I'm dead. Perhaps I can be resuscitated. A doctor is going to come along and they're going to use a stethoscope or an ultrasound to measure whether my liver is still operating, to measure whether my heart is beating, to measure perhaps even whether there are still electronic signals in my head. He may decide, the doctor may decide, that I'm half dead, that I can be resuscitated, I should be taken to hospital as soon as possible, ambulance, etc. And even if I'm put in a box for long enough, I will likely be half dead. That's different from being dead with probability half. Can a doctor revive me? There are measurements for that. We can ask whether I'm alive or whether I'm dead, and those are just opposites of each other. This operator, acting on a vector which has 1, 0 in it, will say, yes, he's alive. Or, no, he's not alive. But there are other operators that can act on the same thing. Is Peter half dead? Well, yes, he's not dead, he's not alive. We can resuscitate him. The opposite of that is something which looks very similar to this, and its relationship is something I'm not quite sure how to say. It's not the opposite in quite the same way as alive or dead. Nonetheless, this is formally an object that we can think about how we would talk about it. Clearly, there's much more to whether I'm alive or dead than just two dimensions. Yes, live, yes, dead. We can discuss many, many other aspects of my existence. When we have incomplete information, non-commutativity is one useful way of encapsulating data that isn't encapsulated explicitly. We're not going to talk explicitly about whether my heart is beating. We're just going to talk rather vaguely about whether or not I can be resuscitated. Now, of course, this isn't quantum mechanics. There's no h-bar, there's no imaginary, but it is a perfectly reasonable classical use of non-commutativity. This makes sense. Half dead? Yes or no. So whenever there are interventions that have complicated consequences, it's worth doing the equivalent of quantum state tomography, finding a complicated state. It's something that makes classical sense in an information theoretic sort of way. This is something that indeed happens inside machine learning all the time in a rather different way from the ways that we have to discuss quantum mechanics, but nonetheless, matrices and so on are very much part of the machinery. Now, even more to engage with a field theoretic way of talking about experiments. And this in particular is Gregor Wies's experiment for the middle 1990s, where this was one of the really categorical experiments to demonstrate the violation of the Bell inequalities at the time. If we're going to think in terms of field theories, then boundary conditions are going to matter differently. We're going to think about this more as the heat equation because there is noise. Then we're going to think about this in terms of particles bouncing off the sides of the apparatus. That kind of bouncing doesn't really feel the whole boundary. Whereas the heat equation knows everything about the boundary. The final equilibrium state will depend absolutely on whether everything is exactly as it is. If you change one part of the boundary, that will change the whole consequences for the solution, the long-term solution of the heat equation. So QFT, I think, is better thought of as an analytic classical thermodynamics than it is thought of as a classical particle physics. So Gregor has this schematic in his thesis in the late 1990s, this is slightly different from that because the labels are all in English instead. This is something he sent me when I asked him for permission to use this. He talks in particular about there being a pump here. He doesn't talk about shoveling particles into the apparatus. He pumps the apparatus. He pumps the electromagnetic field, I will say. As a consequence of which, these two avalanche photodiodes have different events in them than they would if this pump wasn't operating. They also have different statistics than you would see if this modulator was not in here as well. This modulator changes the polarization properties of the light that goes through it, that is part of this whole apparatus, so that the events happen in these two devices slightly differently. And the setting for this modulator comes out of a random bit generator here. Now, the second thing I really like about this schematic is that Gregor is absolutely explicit about what he stores as a result of the signals out of these two devices and the signals out of this random bit generator and out of this clock. He stores the time at which an event happened. He stores a bit that says which of these two devices the event happened in, and he stores a bit that says what the random bit generator was at the time. And he does that both for Alice and for Bob. So, Gregor's got these measurement results. The real data actually looks exactly like he says here. There's a 64 bits, I think, for this, and there's 2 extra bits, and that is precisely what you find in the data sets. What we do for the analysis is we take Alice's time here and Bob's time here, and if those are very close to the same, we create a new entry in a new data set, where the Alice's time is one column, and then the second column is the difference between Alice and Bob's time. And then we have 4 bits for both Alice's 2 bits and Bob's 2 bits. Now we plot the points in that new data set by taking Alice's time along the x-axis and the time difference along the y-axis. So this is 10 seconds from beginning to end, and this is just 6 nanoseconds from top to bottom. Very, very compressed on the x-axis. Then, because there are 4 bits, we use 16 different colors to represent those four bits, where along the diagonal corresponds to Alice's bits and Bob's bits having the same values, and off diagonal, obviously not so, but with different colors depending on how far they are off the diagonal. Now, making that bigger, if you look in the PDF of this talk, you can see every single one of the 15,000 coincident event pairs there were for this particular run of this experiment, where there were almost 400,000 avalanche-Schroeder diode events in total for Alice, but only 15,000 coincident event pairs. And indeed, when those events are very close to each other, within a nanosecond inside this central zone, then the majority are green or yellow, and that is what will turn out on the next slide to be the sign of the violation of the Bell inequalities in this particular color scheme. We can also just for a moment think to ourselves, what happens if we scale this up by a factor of 100 million? Then that's equivalent to Alice seeing one event per hour on average for 45 years, and once each day on average. Bob, 50 million miles away now, will see an event within plus or minus 1/2 second. This is something that is just remarkable. No matter whether you think it can or can't be modeled with classical physics is irrelevant, it's still remarkable, because 1/2 second is much, much less time than it takes light to go 50 million miles. Turning that graphic on its end and taking 100 vertical slices through it, we can obtain these 16 histograms of when events happen relative to, and so each one of these histograms is plus or minus 3 nanoseconds. If we add up all the numbers in that histogram, we get these 16 numbers here. Those 16 numbers we can feed into this calculation of 2.714, which is a violation of the Bell inequalities. So you see here that we have completely classical data, we've applied a completely classical algorithm to it, and we have said that classical mechanics cannot model this experiment. Quantum mechanics uses non-commuting operators to model this violation of Bell inequalities. This is something in the literature only really after 1982 for fine and in a very nice mathematical way in Landau, and I try to present that as nicely as I can in a section of my Annals of Physics 2020. Classical mechanics has only commuting operators, so it is, I suggest the name we should apply to this is computationally incomplete. CM+, we've added non-commutativity into it. It's all just about Hilbert spaces, just as quantum mechanics is, and it can do exactly the same mathematics as quantum mechanics. This is not beyond CM+. So just to show you what this calculation looks like, in Landau in particular, suppose we have 4 matrices, all of which the square of them is equal to 1. What that means is that the eigenvalues of each of those 4 matrices are plus or minus 1 only. And then we enforce that Alice's two matrices commute with Bob's two matrices. What we can do is we can construct another matrix as the sum of products of those four matrices. And then we can consider the square of that. The square of this, when we multiply it all out, has 16 terms. 8 of those terms cancel. And we're left with 8 terms that can be written as 4 plus the product of these two commutators. Now this, the state applied to this operator C is precisely what we have in the previous slide for this expression from the experimental data, the E00 plus E01 minus E10 plus E11. If those two operators for Alice and those two operators for Bob do commute with each other, then we find that the maximum value for the row applied to C squared is just 4, and so the maximum value for this is just the square root of that, is 2. And on the other hand, if those two operators for Alice and those two operators for Bob do not commute with each other, then we have that this expression must be less than 8. So if we only allow diagonal matrices, which is the traditional classical case, we have the Bell inequalities that this expression must be less than or equal to 2. Otherwise, for CM plus, as well as for quantum mechanics, we have that this expression must be less than or equal to 2 root 2. So with non-commutativity, we can present contextual, counterfactually definite models. CM plus and quantum mechanics are computationally less incomplete than classical mechanics is. Now, there is a story here to be told about locality. I'm going to pass over it for this purpose of this slide. In a few slides' time, I will come back to locality. We have commutativity at space-like separation in quantum field theory and non-commutativity at time-like separation. So commutativity and non-locality are very closely related. And you can also see a discussion of this from a slightly different perspective in this article I mentioned earlier in New Journal of Physics 2011. So now I'm going to talk in a slightly engineering kind of way about what is happening when we turn on the central device, which engineers what the electromagnetic field will be all through the apparatus. Noisy electromagnetic field will be. To begin with, if this pump is not operating right, then we won't see a violation of the Bell inequalities. We won't see distant events which are coincident. But events are coincident. Gregor did good work. He made sure that this all works nicely, and so indeed, there are coincidences between events here and events here, which is to say that the electric currents in here are correlated with the electric currents here. If you know what the electric current is here, that gives you more information about what the current is here at the same time than you would have if you didn't know the current here. There are correlations. Now, the settings from these two random bit generators into the modulators, into Alice's A and B here and Bob's B here, those settings are uncorrelated. And we know they're uncorrelated because they're recorded here. We can check whether they're correlated or not. If we found they were correlated, we would say, go and do the experiment again. Clearly, you're not doing the experiment right. And it would take us another 6 months to find new random bit generators that weren't correlated, perhaps. Now, there are correlations between the inner workings of these 4 avalanche photodiodes, which are further away from the pump than are the electro-optic modulators. So we should expect correlations between the inner workings of these 2 electro-optic modulators. By no means can we say because the value is 0, that means that everything is exactly the same inside Alice's electro-optic modulator, except for that single bit being different. We should expect correlations between the inner workings of the 2 electro-optic modulators, just because there are correlations between the avalanche photodiodes. But there's another reason too, which is rather classical, and that is that these inner workings of the electro-optic modulators are designed to act on these noisy electromagnetic field everywhere, so that we get different kinds of events in these avalanche photodiodes. Just because these electro-optic modulators are designed to change the electromagnetic field, so also the noisy electromagnetic field should action and reaction, classical Newtonian third law, should also react on the inner workings of these two electro-optic modulators. Now I'm going to breeze through this, but the uncontrolled details of Alice's and Bob's measurement settings are correlated, this means. We cannot, unless we measure it, assume that these results aren't correlated. Alice's in the inner workings of this and the inner workings of this are correlated. When there are currents here, there will be more likely to be currents here, etc. With that existence of correlations between those measurement settings, the uncontrolled details, Bell inequalities can't be derived for noisy classical fields. And you can find the argument as I have it in Bell inequalities for a random field in an article in 2006. Now, I find it really fascinating to consider this from an engineering perspective, even in more detail. So we have this set of histograms as I showed you earlier. And instead of adding them all up to get 16 numbers, which we put into a violation of Bell inequalities, we can, for each slice, compute the violation of Bell inequalities, which is given by this graph here. So, as you see, the violation in the central region is pretty close to the violation of the Bell inequalities, 2√2. And then, as we go further out, so the noise becomes less correlated and the violation of the Bell inequalities is kind of all over the place. Now, this is actually information as much about the details of the clock, details of the experimental apparatus, exactly how the polarizers are aligned and so on, will all play a part in exactly what this looks like. This bouncing up and down is not necessarily about what we would usually say are the photons. So this is really kind of engineering approach to how to analyze the apparatus in terms of the frequencies that appear in the apparatus. Now, as well as this plus or minus 3 nanosecond graph, we can also consider a plus or minus 25 nanosecond graph and a plus or minus 100 nanosecond graph. And if we look at the details, we find that there's a little shoulder here in the data here, and also here and here. If only I'd used a color different than yellow, you could be able to see it here too. And in fact, on both sides here. Now, if we focus on the actual data and expand it to the right scale. So this is plus or minus 3 nanoseconds, and so is this, and similarly matched up the scales here and here. You see that there is indeed an extra sort of band here that is reflecting something about the apparatus. If we want to debug this apparatus, to get rid of that, we'd have to do extra work. Looking down here, you see that there is actually a violation of the Bell inequalities that seems to correspond very much to exactly what's happening here. So there's some kind of internal reflection, perhaps. But if we wanted to actually debug this hardware, we'd have to have the hardware back again. If we tried to rebuild this hardware, chances are there'd either be no such reflection, or the reflection, such as it might be, would have a different timescale, because some length would be slightly different in the new attempt to reproduce Gregor's experiment. Of course, no one's going to do that. So this is a way of thinking in engineering terms about the apparatus, is to draw different graphs, to draw different visualizations of the data, and so on. Gregor didn't have, basically was just doing this analysis and didn't have this kind of graphical presentation. It's something I thought of in around about 2010. Now, a third aspect of the engineering involved here is particularly inspired by a signal analysis perspective, I think, and that is that we'd like to know what happens before this moment. Because as you see, over this whole 10-second period, there's essentially a coarse-grained equilibrium. If you took any one 1-second period and another 1-second period, the statistics would be very similar. There's a fine-grained non-equilibrium here, of course, because events are happening very much randomly in each of the 4 avalanche photodiodes, and the random bit generator is going all over the place as well. Nonetheless, there's something to be asked about how this coarse-grained equilibrium gets established. When we have the power off, then there'll be very few events. There'll be very many fewer events in the 10-second period in that case. When we turn the power on, then there'll be almost immediately lots of events because there's actually a distance between Alice and Bob of around about, they're both separated by about 400 meters from the central source. And so just a little bit more than a microsecond later, you'll start to see lots of events. On the other hand, just how fast and just exactly what are the dynamics of the coincidences? Do the coincidences happen exactly at the same time? Do they have the same evolution over time? Or is it slower? Is it faster? But is it also a steeper curve? Perhaps when it actually comes in, perhaps it comes in more steeply, even though it's delayed by seconds even. Similarly, how fast does the green and yellow turn up? Does that turn up immediately when the coincidences happen? Or does it turn up slightly later? Again, what are the rates? What is the detailed dynamics for the green and yellow? What changes as we change the distance? Excuse me. What we're doing here is we're probing non-local propagation experimentally. We should not be talking about whether or not this is non-local without doing experiments. Now, this may not be a perfect experiment, but it's something that's technologically important anyway. If we have a power failure, so we're here, we want to know how long it's going to take to have our Bell pairs available to do quantum computation again. We're going to have to wait for 5 years. If we're only separated by a few hundred kilometers, then that is going to be a problem. We want to know what the details are. Now, more generally, power off to power on is not something special. It's effectively just a modulation of the central source, turning the power off and on in a very slow sort of way. We could obtain comparable information just by scanning across megahertz to gigahertz rate modulations of the central source, those being the frequencies that would be important for knowing something about this, I think. I don't want to dictate to an experimentalist how they should do this. Now, finally, before we get into quantum field theory, let me summarize a little about this. I have titles of previous talks I've given, which I call a dataset and signal analysis and interpretation of quantum mechanics, or of quantum field theory, indeed, for a different talk. Having a new interpretation changes nothing, except our intuition. It doesn't change what an experiment does. The data, Gregor's experiment, will violate Bell inequalities whether I describe it with CM+ or I describe it with quantum mechanics. It does change how we describe and imagine what an experiment does. It pushes us towards a field theoretic explanation instead of just being satisfied with quantum mechanics, with a two-qubit expression, for example. It changes as well what experiment we think it would be interesting to do next. As we saw on the previous slide, to me, that's an interesting experiment. It may not have looked interesting to you before I showed you that slide, and I only showed it you because of signal analysis kind of perspective on this. Nonetheless, all the existing interpretations just don't change. Just because I've got a new interpretation I'm putting in front of you, notoriously, new interpretations can be ignored, and this quite likely will be ignored. New textbooks, the existing textbooks are not going to be changed whatsoever. They're still going to be good for deciding how to construct a model for a new experiment. We're not going to discard quantization and all that just because this kind of description is also possible. More importantly, there are no textbooks for CM+ and won't be for at least 10 years, and perhaps there never will be. Now we're going to take a look at quantum field theory. I'm going to give us some kind of intuition by pushing us quite hard towards signal analysis. If you look in quantum field theory textbooks, in one of the first few chapters, you'll find a decomposition of a scalar field into raising and lowering operators and into Fourier components in terms of the wave number k, which is a four-dimensional version of the frequency, so to speak. Now, this phi of x is not a measurement operator. We can't use it to describe measurements. It's much too singular for that. It's what's called an operator value distribution. But we can construct what I'm going to call an F measurement by smearing the operator value distribution with a smearing function, which in mathematics is very often called a test function. And in signal analysis, you find a very similar idea. It's called a window function. It's also a kind of coarse graining on Minkowski space that tells us where and how big and what shape the F measurement is. Now, this construction is linear. So that means we can write the F measurement as two components in terms of the raising and lowering operators, where both these are linear because this one, the lowering operator is anti-linear in the test functions, and we can also think of this as this complex conjugation as a result of the minus sign here. Now, just to go back to quantum mechanics for a moment, we had measurement operators which were just indexed by integers, m1, m2, m3, and so on. But if we want to make contact with the experiment, we're going to need much more than that. We're going to need also a list of descriptions of how each of those measurements should be done in a particular experiment. So we have now two lists. We have a list of measurement operators and we have a list of descriptions, and we can merge those together into a single structure by taking the descriptions to be an index set itself. And we do that because that's precisely what quantum field theory does. We construct an F measurement by smearing with a test function, and that gives us many different measurement operators in terms of many different test functions. And those test functions we can think of as formal, idealized descriptions of how measurements are not point-like in Minkowski space. Now, this is a kind of unification in the sense that quantum field theory has these measurement descriptions built into itself, and quantum mechanics, algebraic quantum mechanics, we can also think of in the same way. Now, algebraic quantum mechanics is much closer to quantum field theory because it's not thinking in terms of particle properties, it's thinking in terms of just measurements, data sets, and signal analysis, which is much closer to quantum field theory's kind of idea of just making a measurement associated with a particular small region of space and time. Now, to think about now the free quantized Klein-Gordon field, where we can do quite a lot of calculations, we can decompose the F measurement into raising and lowering operators, and in order to make progress, we need to know what the commutation relation is between those objects. And in fact, because of the way we've constructed those operators, that results in a pre-inner product between the two test functions f and g because of the linear construction of f and a g dagger. Now that is a pre-inner product. That means that the pre-inner product of f with itself may be 0, even if f is not equal to 0, which for an inner product we wouldn't allow. So now all we need so we can calculate probabilities in this kind of formalism is this set of 4 equations together with some background knowledge, of course. And I'll show you in a few slides' time an explicit expression, two such explicit expressions for the kinds of for what the pre-inner product might look like for particular quantum fields. But just proceeding with just knowing that there is a pre-inner product, whatever that may be, we can construct for this characteristic function for the F measurement. We can decompose the F measurement into raising and lowering components, and then we can use the Baker-Campbell-Hausdorff identity to construct this product of three factors, and that immediately becomes just a Gaussian expression. So if the test function is real valued, then we can take the inverse Fourier transform of both sides, and we obtain this as the expression for an F measurement probability distribution, and this is the normal probability distribution, which is the inverse Fourier transform, of this. And because this includes the pre-inner product of F with itself as the variance, that does indeed have to be positive semi-definite. Positive definite indeed for anything which is going to have non-zero variance. So as we did earlier for quantum mechanics, we can modulate the vacuum state. We can use the G measurement and its adjoint bracketed around the F measurement generating operator, this one, and that will give us a Fock space that's generated just by the G measurements and the F measurements. So that gives us a Hilbert space by the GNS construction, which is usefully smaller than the full Fock space we're quite commonly used to using, because the full Fock space in fact includes every test function we can think of on Minkowski space, and that is an enormous Fock space, Hilbert space, and there's no need for that for many applications, and indeed for quantum optics we commonly use just a few different window functions, and quantum optics is a field theory of electromagnetism. Now everything I've described on these two slides is entirely local in the sense that the F measurement and the G measurement do commute with each other whenever they have space-like separated supports. But we do commonly introduce the vacuum projection operator. That's non-local in the sense that it doesn't commute with any of these F measurements and G measurements and so on. It's useful, however, because it does give us many projection operators of this form, and we use that very commonly for the S matrix. Of course, the S matrix is itself an extremely non-local object in the sense we start at t equals minus infinity and we end up at t equals plus infinity, and that is certainly as non-local as can be. Now, I find it helpful to think of the vacuum state of a quantum field as a carrier signal, not dissimilar to a radio signal that we use to transmit music over the radio. But in this case, the carrier signal is broadband because all the wave numbers on a forward mass shell, for example, do contribute to the carrier signal. It's not just a single frequency. And as well, we have no information about the relative phases of each of those components that do contribute to the carrier signal. So this is intrinsically a structure which is going to be about probabilistic modulations. Now, we saw on the previous slide that we could compute for the vacuum state, for the Klein-Gordon field, a normal distribution just with variance given by the pre-inner product of F with itself. We can move that probability distribution by applying what I'm going to call a G-coherent modulation, which just displaces that normal distribution by a certain amount by taking a G measurement unitary operator and its adjoint bracketed around an F measurement generating operator, and that gives us, with the inverse Fourier transform, this probability distribution. Now, this depends on the commutator between the F and G measurements. So at spacelight separation, there'll be no displacement in this case. But at timelike separation, there'll be a displacement that depends on how far separated F and G are. So the displacement will change depending on where F and G are in space and time relative to each other. But we can do more than just displace a probability distribution. We can modulate it in much more elaborate ways. And the simplest way we can do so is by taking the G measurement and its adjoint bracketed around the F measurement generating operator and normalizing as needed. And that gives us this probability distribution, which is just when F and G are maximally overlapped. So F and G, the pre-inner product is very close to the pre-inner product of the product of the F and F. When this expression here is nearly 1, then we obtain this kind of probability distribution. When that expression is nearly 0, we obtain something much closer to just the ordinary normal distribution we had before for the vacuum state. So most of space and time will just still be the normal distribution, but wherever there is an overlap between F and G, then there will be this kind of modulation. Now we can introduce much more complicated modulations by introducing much higher degree polynomials in the G measurement. And that will result in as many humps as we like, shall we say, and indeed anything that can be constructed as a Hermite polynomial, and so on. So what we have here is that the pre-inner product here, the 2-point vacuum expectation value for the free quantum field, determines the geometric structure altogether. It tells us what stochastic diffusion and transmission the carrier signal supports, because if we attempt to apply a particular modulation to the vacuum state, that may or may not be rejected, so to speak, by the vacuum state, or it may be accepted and hence cause a transmission to a remote measurement. So indeed, a modulation changes the measurement results anywhere in other places and in other times. Now, as well as being able to just modulate a single probability distribution, we can also modulate joint measurements. And that's what we saw already for Gregor Wyss's experiment, where he modulated probability distributions of the electromagnetic field within 4 separate avalanche photodiodes. Since we can indeed arrange for such coincidences, such joint probabilities, we need to be able to model it using this kind of formalism, and we can do so using what I'm going to call a Wigner characteristic function. I call it that because it's only if these measurement operators all commute with each other that this, when we take the inverse Fourier transform of it, will give us a probability distribution. Now, part of what's going on here is that this is not a deterministic system. If this was a deterministic system, we wouldn't need to talk about joint measurements at all. But in fact, we're only going to be able to do a finite number of single measurements of at particular points, for example, and that's going to be incomplete information. So there's plenty of room for joint measurements to give us information that's not provided by the finite number of single measurements we've actually done. So joint measurements can be informative. It's worth having this kind of thing in the structure, but this is not necessarily something that's fundamental. It could be, it may not be. That is to be determined, shall we say. So the reason I wanted to introduce, another reason I wanted to introduce the Wigner characteristic function is because it does give us an effective presentation of the algebraic structure. So for the Gaussian case, we can just take this expression for the Wigner characteristic function abstractly and use the Baker-Campbell-Hausdorff identities to separate out the non-commutativity factor here and this factor, which when we apply the Baker-Campbell-Hausdorff identity again, will give us a Gaussian noise term. So now we have Gaussian noise term and non-commutativity term that determines the algebraic structure for the Gaussian case completely. We don't need any other information to compute any Wigner characteristic function. Now, that doesn't fix the geometric and dynamical structure. We want to do that in many different ways. And just for two examples, we have for the Klein-Gordon field, for a scalar field, we have the pre-inner product of f and g is a projection to the forward mass shell, and then we take the product of the wave number components at each wave number within that mass shell, and we use this constant, h bar, Planck's constant, tells us what the amplitude of the noise will be, since the pre-inner product of f with itself does determine the amplitude of the variance of the f measurements. So for quantum optics, we have something rather similar. We have a pre-inner product, but now in terms of bivector valued test functions for this particular presentation of quantum optics, where we project to the forward light cone, then we construct two space-like 4 vectors, both of which are orthogonal to the wave number. And because they're both orthogonal, this construction is also negative definite in this case because of the choice of metric that I'm using. And so we introduce a minus sign to make sure it's positive definite. And again, we have Planck's constant as the amplitude, the variance for an f measurement. Now, both of these constructions are positive frequency because of the positive, the restriction to just positive wave frequency here. And also both of these are manifestly Lorentzian translation invariant. And of course, both of these properties are required for us to say that this is a standard quantum field theory. Now, what we've got so far does not give us the Gaussian Fock space. For that, we have to introduce all possible test functions generally in terms of short space, for example. And that gives us that has to be done using a direct or inductive limit, as it's called by mathematicians, that allows us to construct a representation space of the Poincare group, which is a much more elaborate structure than just having a few things, which is enough for engineering. So now non-commutativity, having introduced it here, we see that if the f measurement and g measurement have space-like separated supports for those two test functions f and g, then we say they're causally separated, and in that case they are compatible measurements, and hence we discover that this expression, for example, is a correlation coefficient, is real valued, and so on, and within the range -1 to +1. Otherwise, if the test functions f and g are time-like separated or light-like separated, then those measurement operators will be incompatible. This expression, the same expression, will have an imaginary component. So we can't think of that as a correlation coefficient in any direct way. But in fact, we do measure correlations at time-like separation. So in signal analysis, we talk about autocorrelation functions, for example. In that case, we would perhaps use collapse, or perhaps we might use just the super-Heisenberg picture and just insist that all our measurements commute with each other and know that we can construct an equally good model, but just in a different algebraic structure. So we can indeed construct what I'm going to call a quantum non-demolition field theory when we come to it much later in the talk, after about slide 66, I think it is, that is empirically equivalent, for which an FQND measurement and a GQND measurement are always compatible. And then because those are always compatible, we don't have any contextuality, non-commutativity, and indeed we have to introduce something like the Poisson bracket, but in Minkowski space, to allow ourselves to construct transformations, or we can introduce transformations directly, or we can use the vacuum projection operator. There are multiple ways to do that. And it's quite natural to introduce non-commutativity once you know that it's something that's useful and that is classically comprehensible as contextuality. So what we've done here is we've folded into the formalisms of quantum mechanics and quantum field theory only the quantum noise aspect of causality. So whereas we might indeed have thermal noise described in a similar way to quantum noise, we do not. We explicitly model thermal noise, but we implicitly model quantum noise by making it inserting it into the commutation relations. So it is quite natural to think to ourselves, well, there's no real reason why we shouldn't also take the quantum noise and model its consequences directly, explicitly as well, just as we would with thermal noise or any other aspect of causality. And indeed, that becomes something that we will want to do once we get to quantum gravity, where causality may be dynamic, as we see when we have something like gravitational lenses, where the causal effects of that can go by different paths and arrive at the same time and in the same place. In that case, I think it's reasonable to call this a convention in which we have either quantum non-demolition field theory or quantum field theory, whichever seems the better one or the better, more useful case for a particular application. So now we're going to start moving towards interacting fields, not merely the free fields that we can talk about relatively more straightforwardly. We've seen already that for a Gaussian field, we can write down this expression explicitly, and indeed we can compute it. This is a generating functional form of what's called, for the Weightman axioms, the Weightman functions. The Weightman functions just is for this form where we have the f measurements not exponentiated, so to speak, not constructed in a generating functional form, but this can be equivalent to this for at least for engineering purposes, shall we say. So then we can use the Weightman reconstruction theorem, if we're given the Weightman functions, to construct a Hilbert space. And that is just a kind of a more specific version of the more general GNS construction we used earlier, where we build in as well aspects of the Lorentz group and so on that are explicitly mentioned in the Weightman functions, which we'll see on the next slide. So indeed, from a classical perspective, it's not clear to me that there's anything more we could know then all the joint probabilities for any measurement we can think of, any measurement we can describe, we can say, well, I want to know what the probability is. And a theory that's sufficiently careful will indeed be able to tell you this kind of probability, joint probability, and hence conditional probabilities, and hence can predict for the future what you expect, given that you know that the world is in a particular state now. Of course, that's conditional on the world actually being noisy. If the world is deterministic, then we can know more than just joint probabilities. But my feeling is that there's no way we can know whether the world is deterministic or not. And if the world is deterministic, we can just use zero variance in the places where it is actually deterministic. So for an interacting field, all we want is to deform this structure here, the free field structure. We want to have some different function of the lambdas and some different functional of the test functions. And we want to specify that as clearly as we can. What we know is that a Lagrangian deformation is not well defined in 1 + 3 dimensions. And so we want some kind of alternative way to deform the free field case. So the Weightman axioms, which I've been thinking about in various levels for 30 years, seem to me extremely simple. They are just this set of six rules, as you will find, for example, in Haag's Local Quantum Physics, which is a fairly standard textbook for axiomatic quantum field theory. But after 60 years or more, there are no known well-defined interacting models in 1 + 3 dimensions. So it seems natural to me to ask, how can we weaken the Weightman axioms? We might also ask whether we can construct something completely different, but whatever we introduce presumably will include something like the Poincare group at some level. So to look at those axioms, we have, for the Wightman axioms, a Hilbert space we start with, and that supports a unitary action of the Poincare group, so that if we have a specific vector in the Hilbert space, we can move it to a different place, or we can rotate it, or we can boost it. And there's also a unique lowest energy Poincare invariant vacuum vector, so if we try to move that, or try to boost it, or rotate it, we get exactly the same vector. It doesn't change under those operations. Now, to construct something more, we introduce quantum fields as measurement operator valued distributions, which are linear maps from the test function space to an F measurement, which is in the star algebra of measurements. Those measurements support an adjoint action of the Poincare group, so just as we have a unitary action of the Poincare group here, we use the same operators in an adjoint action, so we have the unitary and its adjoint set around the F measurement, and that gives us the same measurement but in a different place, or rotated or boosted. Now, microcausality just says that there will be commutativity at space-like separation, so that one measurement does not affect another if they're at space-like separation. That's really a loose way of saying that, of course. Completeness is just to say that the action of these F measurements on the vacuum vector generates the whole of the Hilbert space. We don't need to know that there are no other vectors in the Hilbert space that are generated by some other operators. Now, time slice axiom I'm not going to talk about. There are, because I will talk about that a little later, there are two linearities implicit in these Wightman axioms. There is the first one, which is von Neumann linearity, as I called it earlier, which we need to ensure that there is a probability interpretation, just as we needed it for quantum mechanics. And I don't propose to mess with that at all, because a probability interpretation is just too useful to give up. On the other hand, there's also another linearity which is implicit in the choice of defining a measurement operator value distribution as the way to construct measurement operators. So it makes the F measurements axiomatically linear in the test functions because of this construction. And that results in this linearity as well as this other linearity. Now, when we look at renormalization, I'm going to argue over the next 5 slides that for that reason and for others, we really should allow quantum fields to be nonlinear maps into the algebra of measurements. So this map to the F measurements should not be enforced as a linear map. And so we will not have this linearity as well as the von Neumann linearity. Now, I'm going to start a little slow. I'm going to talk about, in rather vague terms, about signal analysis, where we might say that f of x and g of x are window or modulation functions. So we'd have a modulation over here and a measurement over here. And we would think of the pre-inner product of f and g as something like a resonance between those two, but a stochastic resonance, where we have indeed the modulation and the measurement as a pair. If we were talking about signal analysis, then linearity would just be the first approximation. We would expect that in more complicated cases, if we want to consider the physics more carefully, we would expect there to be nonlinearity emerge fairly quickly. And so, from a signal analysis perspective, linearity of the field is just not so obvious that it should be axiomatic. And so I think we should talk about the Wightman axioms both in linear form, as we have done, but also in terms of a nonlinear form, where we allow the F measurements to be nonlinear functions of the test functions. Even more generally, if we were talking about something outside of physics altogether, we might say, well, we have a text descriptor, this text measurement, text 1 measurement and text 2 measurement and so on. All we need to construct a statistical model for that, that's Gaussian at least, is to introduce a matrix that takes for each pair of text descriptions and takes each pair of text descriptions and constructs a matrix entry. And so long as that matrix is positive semi-definite, which is a structure known in mathematics and computer science as a kernel, which I'll talk about considerably through the rest of the talk, Then we can construct a Gaussian model. We can do statistics for a Gaussian model. For more elaborate models, we'd have to do something more. Now, I don't think either of these two discussions constitute a strong argument, because we might indeed want to say that a fundamental field should be linear. But if we look at real space renormalization first, we find that nonlinearity does appear in real space renormalization. If we suppose that a test function is defined on just this small square region, it's a smearing function on that small square region, we split it into 9 fragments, which add up to give us the test function we first thought of. Then we do the fj measurement in each of the 9 regions we've now constructed, and we decide whether the result is positive or negative. And then we say, well, +1 or -1 is the result. Then we add those all together, and we decide whether the result of that is positive or negative, and that will give us -1 in this particular case. So now we have this 9-fragment f measurement. What real space renormalization does is it iterates that many, many, many times, even an infinite number of times. And so that construction of a fragmented f measurement is clearly nonlinear in the test functions, and it's clearly different from what is often called the bare f measurement, which is inaccessible in the ways we talk about effective field theories. Nonetheless, we imagine it being there. But we also talk about the dressed fragmented f measurement, which is arguably still in a quantum field, because if you talk about effective field theories, for example, indeed we have pretty much this construction is taken to be a quantum field of the sort appropriate for effective field theory. So I think that's a slightly better argument, that we should allow and expect an f measurement to be nonlinear in the test functions. Now, if we look at the renormalization group, it's a slightly more complicated argument, but nonetheless, we come to a very similar conclusion. So I'm going to take a description in the first chapter of a book by Hollowood in 2013 about the renormalization group, where he suggests that a measurement f is a function of interaction parameters of some characteristic length scale that tells us where what the measurement is that we're performing, and also of a particular choice of cutoff. Now, if we choose 2 different cutoffs, mu and mu prime, that gives us 2 different theories. And because both theories, however, are trying to describe the same situation in reality, in real measurement results, those 2 should be the same, even though we've chosen a different cutoff. Now, to me, this idea that a single characteristic length scale should be something that defines what the measurement is clearly unacceptably vague. We want to consider what the measurement is in much more detail than that. And if we did do so, then we would write experimental results, perhaps, as functionals of test functions, or of something similar, some other kind of description of what each measurement, what each component of this measurement is. And so we replace L by a list of test functions. Now, I think of this list of test functions as pretty much a complete description, at least in a formal sense, of an experimental apparatus. It's not different from entering a bunch of numbers into engineering software and deciding whether or not a particular engine works or not, or is likely to work or not, before we actually construct it. And indeed, sometime in the future, we can hopefully enter a lot of test functions, much more elaborate sort of structure than just numbers, and that would allow us to predict experimental results for an experiment which we are not actually going to construct, perhaps, when we discover it won't work. Now, not only is the characteristic length scale unacceptably vague, it's also rather vague to say, well, there's a cutoff scale. And you might say, well, 10 to the minus 10 meters is appropriate for this experiment, 10 to the minus 5 meters is appropriate for this other experiment. Clearly, we should be doing something more precise than that, more detailed. We should be also depending on the details. So we should write the cutoff choice as a functional of the test functions which describe in detail what the experiment is going to do, what the particular measurement is going to do. That also, because of the way that Hollowood has constructed it, at least fixes an effective dynamics as a function of the cutoff. So hence, we can take all this dependence on the test function and absorb it all into a new description, a new measurement, an f, just as a function of these, and just forget about mu and lambda altogether. So now, this construction, however, is certainly more nonlinear functional of the test functions than we had perhaps up here. Even if this was linear, this now is certainly not linear. Renormalization becomes the essentially trivial statement that f prime equals f for different cutoffs. Now that's a more complicated argument, I suppose, but the end result is just the same. We're going to allow and expect an f measurement to be nonlinear in the test functions. Now a rather different kind of argument comes from holism. Because after all, if we consider an f plus g measurement, and that is not the same as an f measurement plus a g measurement, then we can think of the difference between those as one measurement of how much what is measured by an f measurement interacts with what is measured by a g measurement. Now, what is measured by and the measurement itself are different things. So when we talk about this expression being not satisfied, this is in a sense measurement and modulation holism. The measurement is not the same as the sum of its parts. It's slightly different from what is measured holism. Nonetheless, I suggest neither of those should be excluded axiomatically. We shouldn't say holism is impossible. By axiomatically, it's obviously impossible. We can't have that in our theories whatsoever. Well, we should sometimes perhaps use that because it simplifies, but nonetheless, occasionally we should indeed allow and expect an f measurement to be nonlinear in the test functions. Now, you can find an argument to pretty much this effect in a recent companion article in the Philosophy of Physics, this article by Laura Reeh-Schlieder, where she points out that strong additivity, which is essentially linearity within the rather more abstract Haag-Kastler axioms literature, is a precise way of framing in algebraic terms the idea that the whole is not greater than the sum of its parts. Now, I want to emphasize that although she's not distinguished here, I wish to distinguish strongly between the whole measurement not being the sum of its parts and the whole what is measured not being the sum of its parts. This is a mathematically much better defined object because we're not taking powers or products of operator value distribution to talk about this object, whereas for this we very commonly do when we shouldn't. So finally, as an argument towards introducing nonlinearity, if we have in fact got an f measurement that is nonlinear in the test functions, then we can use functional derivatives of that object to construct, in this case, a two-point operator value distribution. Now that's something that is very definitely not present in the Whiteman axioms. This is quite an extreme modification of the Whiteman axioms in a sense. Nonetheless, you can actually find Wayne Polizu and his collaborators, for instance, even in the 1990s, suggesting this kind of structure as a way to model bound states. And indeed, that seems like it might be a natural sort of thing to do. Secondly, if in fact not only is the f measurement nonlinear, it's also not expressible as a function of Taylor series, which would be the case even if we just have something as simple as a cutoff using a hyperbolic tangent applied to the test function, for example, then test functions may wrap around the singular points of such constructions. So for this particular example, there are singular points on the imaginary axis, and particularly, for example, at j pi over 2. That potentially is going to result in discrete structure as things wrap around those singular points. Not clear to me exactly how that works. Nonetheless, this is something that going forward would be certainly something to consider, I think. Now, you can also find something a little similar to this in literature about the Wilsonian renormalization group flows. And this particular example is in the context of quantum gravity, where they present a complicated argument that the space of rescaled correlators is similar to that of n-variate distributions. In other words, essentially this. Now, perhaps we could get away with just multilinearity. But I think the reasoning on the previous slides really allows us to only say nonlinearity. This possibility suggests we ought to retain the possibility of nonlinearity as perhaps a tool towards introducing discrete structure into quantum field theory in a new kind of way. So, what I think I've done is I have established that renormalization and a few other arguments push us towards introducing nonlinearity into the Whiteman axioms. Now, to go further than that and to show you how that is actually going to give us enough power by that weakening of the Whiteman axioms that we can reproduce anything that is done with Feynman integrals, for example, Feynman loop integrals, for example, I'm going to have to introduce you to the Reeh-Schlieder theorem. And in order to introduce you to the Reeh-Schlieder theorem, I feel that I need to give you some kind of intuitive grasp of what that might be about. Because, in fact, in the literature, there is a considerable amount of consternation, even, about the kinds of nonlinearity that is introduced by the Reeh-Schlieder theorem in the context of the Whiteman axioms, which do not immediately look very non-local. And so, stepping even one step even further back, I'm going to talk about the classical Klein-Gordon field and retarded propagators for that first. And that is a distribution-valued solution of a classical inhomogeneous Klein-Gordon equation, but because there is this Dirac delta function on the right-hand side for this Klein-Gordon differential operator. And because there is this Dirac delta function on the right-hand side, we can have solutions of this equation which are zero at space-like separation and are negative in the past, whereas in the future, the retarded propagator is non-zero. So this has a rather singular structure on the light cone, on the forward light cone, but is a perfectly reasonable function within the forward light cone. When we look at the two-point vacuum expectation value for the quantized Klein-Gordon field, however, which is the appropriate object for a discussion of the geometry in the sort of textbook sort of way, where we would have an expression such as this, you will find, where the two-point expectation value can be centered on zero because of the translation invariance of the vacuum of the Klein-Gordon field, and that we can write down as this expression, which is just the same expression as we had for the pre-inner product earlier, but with the two test functions replaced by delta functions effectively. This vacuum expectation value is a distribution value solution of the homogeneous Klein-Gordon equation. That's to say there's no Dirac delta function on this side, and that imposes upon us a real consistency constraint that results in not being able to take the vacuum expectation value to be zero at space-like separation, for example, and certainly not at reverse time-like separation, consistently with this being a positive semi-definite construction. Now, just to show you what these Bessel functions actually look like asymptotically, which I think is helpful, if we consider it at space-like separation, we find an exponential decrease with increasing space-like separation. So that's very similar to the kind of thing we have in thermal physics, classical thermal physics, but with an extra component here because this is the Klein-Gordon equation after all. For the forward and backward light cones, we have something slightly different. We have the same expression in terms of the separation to the -3/2, but where we have a minus sign here, we have an imaginary here. So this is an effectively sinusoidal transmission almost. This is a little different from a regular transmission because there are many different wave numbers contributing to this transmission, because this doesn't restrict to just a single frequency. And that's why this looks rather different than it would if this was just a radio transmission at a single wave number. So the way I think about this, what this does for us, is that when we want to change our model of an experiment, so we're going to apply a modulation to the vacuum state. So we're going to apply a modulation that corresponds to introducing a new piece of apparatus at a particular place. When we do that, we can't just introduce it and then ignore the past, ignore the present, we can just think about only the future, perhaps. Not so. Because of all this analytic structure that we've imposed here, we have to change what happens in the past. We have to introduce the parts that become the apparatus here, essentially. And because we have to change the past so that the present looks the way we want it to, that also has consequences at space-like separation. By changing the past here, that changes the present as well. and everything has to be consistent, these things together. So the way to put this in very brief is to say there's no deus ex machina for this kind of model. Of course, you can have a different kind of model, though probability theory really imposes quite a strong constraint here, in which there is a God that just inserts an experimental apparatus wherever they like without any worries about consistency. But for this kind of model, yes, there is no deus ex machina. Now, as you've seen, the two-point vacuum expectation value here fixes the geometry of the quantized Klein-Gordon field completely. This structure is all that we need to know for us to be able to construct what the geometrical consequences are of any particular imposition, any particular modulation, and any particular measurements we might perform on that modulated vacuum state. So if the geometry is complicated, it's because of those properties. Okay, so that puts us in a position where I hope that we have enough of intuition that we can look at the Reeh-Schlieder theorem and not be too scared of it. We have the Reeh-Schlieder theorem asserts that for a free Wightman field, as we described earlier, we can approximate any vector by applying just local operators acting on the action of only local operators on the vacuum vector, this V. And the reason why that theorem holds is it's a consequence of the analytic structure of this kind of model. There is no deus ex machina, and so everything has consequences. We can't just ignore what might have had to happen in the past, so the present is as it is now. Now that approximation is in the sense of the Hilbert space norm, just to go into details for a moment, so that if we construct a modulated state, a vector of this form by using an arbitrary operator x, so long as that vector is of finite norm, so it's in the Hilbert space, and for any choice of epsilon, so however small that is, then we can find an operator that is in some small region only, that only has support in some small region. Then we can find such operators for which the difference between the vector we first thought of and something we can construct entirely locally is very, very small as we like even. Now, there are limitations to this. This is not a get-out-of-jail-free card for quantum field theory and for non-locality. First of all, the vacuum vector is an extra special case in a dense set of special cases, but for almost all vectors in the Hilbert space, we can't approximate x hat of psi using some local construction in terms of starting from the vector psi. And even more, perhaps more clearly, in general, we can't in the operator norm take an operator x and approximate it by some a that only has local support. So what we can't do is we can't exactly perform remote measurements. I can't here perform a measurement of what someone light years away is doing right now. I would have to wait for results, etc. So on the other hand, modulation can make remote changes because it uses the analytic structure to enforce that the present space-like separation is as it wants to be, because indeed we're going to change the past and that can change the present. So now we're going to use that theorem on this slide. We look at elementary textbooks, we'll find that the Lagrangian deformation is applied to a free Wightman field, for example, by introducing this expression here instead of just having JMJ as we did before. And so we have a modulated form of a deformed version of the measurement of the J measurement operator. So that we can write in terms of the Zj as just this time-ordered expression here, and that gives us this expression, which in terms of a test function J, although we call it a source, nonetheless, mathematically, it's just a test function, a smearing function, which we apply to the modified J measurement or to just the J measurement for the free field. But if we try if we require that a generating function is constructed in a Lorentz invariant way, then we find it's not well defined. And indeed, this operator, the Jz, applied to the vacuum vector, is not in the Hilbert space. So what we're going to do is we're going to apply a regularization for which that vector is of finite norm. And because it's of finite norm, we can apply the Reeh-Schlieder theorem. So we can approximate that vector by a vector that we construct purely in terms of non-linear local functionals of the J, and that will, where we require that the supports of these fragment functionals, as I'm going to call them, applied to the source function is a subset of the support of the source function we first thought of. And that is why I call it a fragment functional, because of this support condition. Now, effective field theories and renormalization introduce a complication here, and that is they introduce mass and length rescaling. But that is just a matter of rescaling masses. So we can accommodate that by just using fields of different masses for different functionals. So instead of having the same operator value distribution, but now, well, actually, yes, linear operator value distribution M hat, we can have a different such thing for each fragment functional. So in fact, this is an operator value distribution still at this point. By the time we get to the next slide, everything's going to be start to get much more nonlinear. So we know that we can approximate the physics with a regularized effective field theory. And we know from the previous slide that we can approximate that by a local nonlinear construction in terms of the source field. And consequently, we can hope at least, and perhaps we've shown even, that we can model the physics with this kind of construction as well. So if we think for a moment about what the 4-point vacuum expectation value, time ordered, for the usual sort of construction, what that looks like, then I'm going to smear it by 4 different test functions so that we can fit it within this box. And having fitted within this box, we have that we take the 4 test functions and then we construct a loop integral where there are many internal degrees of freedom which we integrate over the whole of space and time to construct this. And of course, that is a singular construction unless we've regularized it in some way so that it's no longer Lorentz invariant. On the other hand, if we do the same sort of construction of a time-ordered vacuum expectation value for a 4-point vacuum expectation value, then that will come out to be the sum of many products of nonlinear overlaps, as I'm going to call them, of these fragment resonances between the fragment functional F1 applied to the test function F1, the fragment functional F1 applied to the test function F3, and then we'll consider the overlap, the pre-inner product of those 2 fragments of F1 and of F3. And we'll construct many other fragments as the part of the construction for this, and I'll show you some details about that in a few slides' time. So this is kind of a many-fragment resonance between these many different components, but this is a local construction in a sense. The only non-locality is this relationship, pairwise relationship between the measurement operator and the resonance, and between these 2 measurement operators. Excuse me. So this is non-constructive. So this is not something easy to work with. It's an inverse problem. We were looking for a local nonlinear, many local nonlinear fragment functionals and measurement operators using those fragment functionals, and we want to locally approximate, locally in the sense of this kind of construction, what happens in the bulk for these path integrals. And all that works because of the analyticity that comes and allows us to prove the Reeh-Schlieder theorem for the Weitman axioms. So you might feel that this is too far from here, but I suggest this is very similar to what we accept quite happily with holography, where we take the boundary to determine what's happening in the bulk. In this case, we take what's happening in just these 4 small regions to determine what happens in the bulk in this sense. So there's an interplay between local and global, which is in that similar, because it's about analyticity, to holography. So now we've analyzed renormalization, which suggests we should introduce local nonlinearity, and we've analyzed path integrals, and that I think has suggested as well that it's enough to use this kind of construction. Now, not only that, we can also do better than just approximating regularized interacting quantum field theories. We can explicitly construct, which I'll show you in a few slides' time, Poincare invariant interacting quantum field theories within this modified axiomatic structure. So what we have here is we now got, hopefully, in some point in the future, we'll have a function of these lambdas and a functional of these test functions. There'll be some entirely classical functional of those lambdas and FIs. Because it's just classical mathematics, we can decompose that in many different ways, in terms of wavelets, in terms of Fourier transforms, in terms of, well, whatever kind of decomposition works well, whatever gives us good intuitions about many different experiments. We want a formalism, a choice of decomposition or of how we construct these things, which works nicely without introducing lots and lots of epicycles. We want perhaps to have 2 or 3 epicycles, not 200 epicycles, to get a good prediction for experiments we care about. Now, the old school way of talking about this is to say that we want to carve nature at its joints. I certainly want to do that for all that everything here seems very instrumental. This is something where I step back from instrumentality and I want there to be a really nice, something I can really get hold of and say, this is real. Now, everything I've done here has been in terms of the Wigner characteristic function. Mathematicians may well come along and say, well, there's a much more elaborate mathematics than that, which will give us much better intuitions about what's happening in different experiments. We'll use that instead, and I look forward to seeing it. I'm by no means stuck. Well, I'm stuck, but if someone shows me something better, then I'm absolutely would be very happy to see something more better than this kind of really quite elementary structure, in some ways just a generating function. So what I think axioms look like for quantum field theory now, not to take the Weinmann axioms as really the very starting point, and really to take an engineering and data analysis kind of perspective, I think we start with measurement operators, some finite set of measurement operators, which are nonlinear in these test functions on Minkowski space. Isotony is a term that comes from the Haag-Kastler axioms, which just means that if we have a small set of test functions that gives us an algebra, then a larger set of test functions should give us an algebra that just is bigger than the algebra. It should be a subalgebra of the larger one, which is a relatively natural constraint and really not difficult to satisfy. We also expect there to be a manifestly Poincare invariant state, so that we can use the GNS construction of a vacuum vector and of the Hilbert space, very much as we saw for quantum optics. Now, we're going to allow mathematicians to construct a representation space of the Poincare group if they wish to, or mathematical physicists, obviously, as well, by using a direct or inductive limit. But if we're engineers, then we won't expect to do that very often. We'll insist on there being some kind of spectrum condition and on microcausality, so that if F and G have causally separated supports, then we'll expect the F measurement and G measurement to commute. Now, just to focus on the test function space for a moment, really, we just don't need or want the mathematical complexity of a representation of the Poincare group. It's enough to have manifest Poincare invariance. We don't need representations of the Poincare group, just so long as we have invariance. And as I've said several times, it's commonplace to just use a small number of test functions. That's an engineering practice, standardly. And so an axiomatic approach shouldn't exclude that. Now, the reason I've not introduced a time slice axiom until now is because it fits quite naturally with the question of the test function space. Because what the time slice axiom says is that if we know all the expected measurement results on a Cauchy surface, that will determine all the expected measurement results in these backward and forward light cones. That is an enormously strong constraint. It's something we would never know for engineering and for most physics purposes. We only know the results of some finite number of measurements. Now, if we know the relationship between those measurements and the relationships between some other measurement, which we perhaps have not yet done, or that we've done in the past, or whatever, but we want to know what the results would be, given that the measurement results of these are what they are, we want a state in quantum field theory to give us conditional probabilities for the measurement fm plus 1 given the results of this thing here. So that's just to talk about joint probabilities. This construction I'm suggesting here is naturally multi-scale and it's multi-time. It's neutral about reductionism because all of these test functions, the ones we start with and the ones we want to predict, can be arbitrary scales and arbitrary time. So we can have a group of measurements here, and we want to know what the result of a measurement would have been in the past had we measured it, or we might want to know what the result of the measurement in the future will be if we measure it. But also, if it just happens that we want to know the result of an extremely large measurement, we can measure F1, F2, and F3, and so on to be within the region that is Fm plus 1. And hence, we take the result to tell us something about the large from the small. But we can also take all of these F1 through Fn to be very large objects and work kind of as a microscope to tell us what the result would be of a very small measurement. So, explicit constructions. I've got 3 slides about this. The first construction is something really quite elementary. We can modify the usual situation, which is just to take this pre-inner product, which is linear in the test functions, and add to it a sum of many different fragment pairings, where the fragments, we construct the kappa fragment for F and the kappa fragment for G, and then we take the pre-inner product for a particular pre-inner product corresponding to that kappa. That will give us a nice kernel, where, as before, we have the supports of the kappa fragment functional should give us something which is within the support of the test function we first thought of. And for example, we have f squared, we have the hyperbolic tangent, we have f times almost anything. And in this particular case, this is a Lorentz invariant propagator in convolution with the test function, and we can have much more complicated constructions. What this gives us is it gives us a sum of many nonlinear binary relationships between many of the different fragments of the test functions we first thought of, and that is instead of taking a sum over many paths, because the paths, after all, go through the space between in a way that we're not going to worry too much about in this kind of formalism. What we have here is we have a modulation, and we have a measurement, and we have something happening between them, which we're going to describe as a diffusion and transmission. We're going to take many, many channels and add them all up to give us the consequent for the 2-point vacuum expectation value and for other correlation coefficients and vacuum expectation values, etc. Now we can do something slightly more familiar in a way by just deforming the time-ordered vacuum expectation value generator. So for this object here, instead of adding into here a Lagrangian term, we can instead add a term of this kind, where we take the source, the test function, and we multiply it by well, as I described earlier, by a Lorentz invariant propagator in convolution with the same test function. If we do that, we find a mathematics that actually can be presented in a Feynman-like way, Feynman-like diagram way. But always, what we end up with this particular construction at least, is something that is always tree level. So we have the J, the incoming J, the incoming G, and the incoming H star G is represented this way with the propagator modifying this incoming line here. And because of the multiplication, that gets represented as the joining of two lines. And then we have the Feynman diagram propagator, the Feynman propagator, because we have the time ordering here. We can introduce much more complicated things of this, but there will never be any loops generated by this particular mathematics. So a second way to approach this kind of mathematics is to use the phi-4 theory as a different kind of inspiration. For that, we have this equation for the phi-4 deformed Klein-Gordon field, but we can present that as an equivalent integral equation, where we use the retarded propagator for the Klein-Gordon differential operator, and we have again the normal ordered third power of the measurement operator value distribution here, which of course makes this a singular construction. But we can use the same kind of idea. We can take the F measurement to be the sum of the free field measurement with added to it a factor, a term that is just the integral over many different fragments, and take the cube of each of those fragment measurement operators. Excuse me for the language. And of course, what this means is that we take a test function f, we construct the f kappa, the kappa fragment functional of that, which is in this region, and then we do that over and over and over again. It's effectively a fractal structure we're constructing here. It integrates over many different fragments instead of over points in space-time. So whereas we have an integral over points in space-time here, we have an integral over many different fragments. And again, this is going to result in binary relationships and nonlinear such things. We'll have a modulation and we'll have a measurement separated by the pre-inner product acting on those, being effectively a diffusion and transmission. That's again going to be a multi-channel sort of construction, but it's also going to be quasi-fractal, so to speak. So this is more elaborate, very definitely not Gaussian anymore. Now, this final slide I include mostly because it just seems like such a lot of fun that there's such complicated things can come out of this way of thinking. We have, for the Gaussian quantum fields, we just required that this object is a positive semi-definite matrix, which we'd call a kernel or a pre-inner product, perhaps, but also could be a kernel in this sense, so nonlinear in the test functions. But it's the case that if we take two different kernels and take the product of them, this product, which is not the matrix product, this is an entry-by-entry product. This construction is also a kernel. It's quite straightforward to prove that that is also a positive semi-definite matrix. Then we can also use sums of terms such as this. And that, straightforwardly, microcausality is satisfied because we have, if this is satisfied, then so is this satisfied. And indeed, we can use products of many different factors. We don't just have to use the nth power of a particular kernel. Even more weird and wonderful is convex hull microcausality. From microcausality, we had that if the supports of f and g are spacelight separated, then we have the commutator is 0. And so for this particular pair of test functions f and g, their supports are spacelight separated, pretend they are, but their convex hulls are not. And convex hull microcausality says that this commutator can be non-zero even if the supports are spacelight separated, so long as one is surrounding the other to some extent, but obviously the explicit statement is in terms of convex hulls. And this is particularly of some interest, almost certainly not physical, but nonetheless mathematically of some interest, because this weaker microcausality is satisfied by a construction as straightforward as the convolution of f with itself and the pre-inner product of that with the convolution of g with itself. So that is such a straightforward sort of construction that perhaps it actually is relevant physically. But I'm certainly not taking any bets. What we have now is we've introduced a lot of structure, but I suggest that so much structure is needed. We're aiming to unify the idea of renormalization scheme with the idea of a generalized stochastic dynamics at all scales. What we usually have is an index set of Lagrangians, indexed by some specification of coarse graining or some specification of a cutoff scale, renormalization scale, and so on. But what we have instead is an algebraic and geometric structure that's entirely determined by the test functions we choose that describe the measurements that we're going to actually perform in detail. So for a deterministic field, it's perfectly reasonable that we'd have something like Lagrangian, and indeed, obviously, the mathematics works out perfectly well for a deterministic field, a classical deterministic field. But we're working with a generalized stochastic field, generalized in the sense that we're working with generalized probability, but also just with the stochastics, probability distributions over the kinds of configurations we'd expect for a deterministic field. It's a higher order mathematics, and so we really should expect there to be much more structure required to specify it completely. So we've introduced these nonlinear axioms. They're definitely weaker than the Weitman axioms. There must be more models. But we've introduced nonlinearity. as well as the dispersion and noise which were there already for the Wightman axioms. We've introduced the possibility of multiple kernels. And so there's the possibility of interference between the results you get for those many different kernels and how they're combined together algebraically. Nonetheless, we're thinking in a rather more classical perspective. Everything is in terms of signal analysis, in terms of data analysis. And so I think because we can say, well, classically, we can certainly engineer solitons. Surely we should be able to engineer solitons also in this kind of generalization of deterministic physics. And there's certainly, we'd expect there to be an idea of caustics, and hopefully there can be models for tables and chairs and for computers and hands and so on. Now, as well, we can hope that measurement outcomes can be modeled as generalized thermodynamic transitions. Because whereas for thermodynamics, as we usually have it, there are chemical potentials and thermal noise, and the ways in which those interact with the particular dynamics of the system give us thermodynamic transitions. Now, we have two types of noise, as I write it here. There's thermal noise and quantum noise, as well as chemical potentials. If this isn't enough, then we should weaken the Wightman axioms even more. Or in a completely different way. After all, there's no guarantee that I've got this all completely right. Or we should introduce completely different axioms, which I have no idea what they look like, but I think there will be some kind of nonlinearity in there. I think nonlinearity is unavoidable, at least according to the analysis of renormalization I've suggested here. So I haven't mentioned fermions at all. I'm loath to say anything about fermions because I don't consider myself to have enough that is at all solid. I console myself that in classical physics we would quite happily eliminate fermionic degrees of freedom and leave ourselves with just the electromagnetic field and higher derivatives on a particular Cauchy surface as a way to determine the future in those sort of terms. And indeed, if we have a model that tells us everything about a deformed electromagnetism at all scales and all times, then we can compute with that what the electric currents are, which after all is just in terms of the divergence of the electromagnetic field. So given that we have all that information, if we knew everything about the electromagnetic field, that would tell us about vortices in the electromagnetic field, perhaps, about various patterns of electric current, each of which will be characteristically more like what we expect for an electron, or more like what we expect for a proton, more like what we expect for other particles, neutrons, and so on. Now, even if the electron, proton, and other fields are essential, I just think it'd be interesting to know, for just the interacting electromagnetic field, what this Wigner characteristic function would look like. It's just going to be a manifestly invariant functional of just the lambdas and the f's. Perhaps, however, we really don't need to know anything about the electron, proton, and other fields. So long as we know everything about the electromagnetic field, perhaps that tells us everything we need to know. Now, in Feynman diagram terms, for this we can think of, rather loosely, of course, by saying that when we have a photon, we would say that it's surrounded by fermions and by clouds of photons and other clouds of other kinds of particles. So loosely, we have that an extreme electromagnetic field creates positrons and electrons. And then we can guide those electrons and positrons to where we want them to be, and we can construct something in the future that looks like a table or whatever it may be. You need a lot of electrons for that, and a lot of other things, and obviously protons and so on. Now, I said up here that perhaps electron protons aren't essential, but perhaps they're not. If knowing all the electromagnetic field measurements is enough, nonetheless, we have only a finite number of such measurements. So just as we saw earlier, doing joint measurements is informative. Doing something that we haven't done yet, that is completely different from an electromagnetic field, nonetheless will be informative. So even if then it's not necessary to know something about the electron and proton, nonetheless, it can be useful to have that as a tool nonetheless. And of course, it is useful. And in the future, I'm sure someone will do much better than I can for such things. Now, quite helpfully, we have from an article in the philosophy of physics literature, this concise list of the difficulties of quantum field theory. It's not necessarily complete, but it's a pretty good list. We have divergences, which I suggest we can get around by rethinking renormalization as something that suggests nonlinearity in the Whiteman axioms or some other set of axioms. There's no precise ontological picture. And I think we can get around that by thinking in terms of data sets, in terms of signal analysis, in terms of classical measurement incompatibility, perhaps. There are no particles is something that has preoccupied philosophers of physics and some physicists for several decades now. But by the introduction of nonlinearity, as well as the dispersion we have, I think there's plenty of hope that we will be able to construct solitons and caustics and so on. Haag's theorem is a rather technical result that says that representations of free field and of interacting fields are unitarily inequivalent. They really don't mix and match well. They're oil and water, so to speak. But by the introduction of nonlinearity, we give ourselves the possibility of constructing subalgebras of many free field algebras in a way that is not included in the sort of considerations that are the basis of Haag's theorem. For the measurement problem, I don't think the situation is any different than it is for quantum mechanics, as we saw earlier in the talk. So I think we can rethink collapse as a joint probability construction. Now, before we go into quantum gravity, I just want to point out that I really have been trying to think in terms of quantum field theory as fields of measurements. It's not about a field that is measured. That's kind of classical and deterministic. This is about fields of measurements and the statistics we get back for those measurements. Those measurements are indexed by metadata, by measurement descriptions, by test functions, whatever you will. Once we've described that field of measurements, then we can talk about what a global state tells us about measurement results for those measurements. And from that, we can infer more about the wider world in a sort of intuitive way that I think can be quite realistic. And I'll talk a little bit more about that later. So, how can we use what we just learned to think about quantum gravity? To start slow, if we're given measurements, just a list of n measurements, all we need for us to be able to do statistics using a Gaussian state is one kernel, as we call it, where we take every pair of descriptions and we construct a matrix for each pair, and that has to be positive and semi-definite, and it's an overlap matrix, as I call it. It's a kernel. If we have, in order to construct a successful deformed optics, then we're going to expect there to be many such kernels. And we're going to expect to combine them in such a way that this rho v prime is a state. And I've shown you a few methods that can be used to do that. This collection of many kernels fixes the geometry, and we combine them in whatever way we do. Now we want to do quantum gravity. So all we need to do in the first instance is introduce a new description which takes the bivector test functions and a background that we want to impose. This is not the background as it is. This is not the background we're going to get. This is a modulation that we want the vacuum to accept. And it may reject it or accept it, and it may transmit it in many different ways, because, after all, it's going to take different fragments and mix them all together so that there will be a propagation of some kind to a remote measurement. Nonetheless, it will do what it will, no matter what we ask it to do. Well, if we ask it well, it will send it well. If we ask it badly, it will just say no. And we can use metric or torsion or non-metricity as we will, whichever formalism works best for telling an experimenter what they need to do for this experiment to work. So now, in this successful deformed optics which we happily constructed in our imaginations, we replace anywhere where a kernel appears, the kappa kernel for the original bivector test function appears, we substitute a different kernel, kappa kernel, for the extended description. And that will give us a candidate quantum gravity version of optics. Of course, the first one we think of is not going to be not going to work. It's not going to be exactly what we want. Nonetheless, this gives us a kind of formalism that I suggest is different from anything else that you can find in the literature, at least as far as I know. It gives us a measurement and dataset theoretic approach to gravity. This is not quantizing gravity because here we are talking about structures intrinsically in terms of the quantum theory, in terms of where there is a non-trivial non-commutativity between operators. We're not gravitizing quantum, nor are we talking about gravitons whatsoever. This whole structure is entirely in terms of this essentially continuous set of preanna products. And of course, we're also not talking about what the structure is at very, very, very small scales, at 10 to the minus 40 meters or 10 to the minus 100 meters or whatever it may be. Nonetheless, this kind of description in terms of kernels can give us predictions about what's going to happen at 10 to the minus 1000 meters even. It's completely open to give us results for that for very, very small scales, just as the free field is. Of course, the answers it's going to give us are not going to correspond to the real physics at 10 to the minus 1000 meters, assuming there is even such a thing. But nonetheless, this kind of model is open to predicting things at all scales. Now, given that I've introduced the kernel as this fundamental aspect of this kind of construction, it's helpful to consider how manifest invariance, substantive covariance, as I'm going to call it, and gauge invariance emerge, can be discussed in this kind of formalism. So we have that if we have the preanna product between two test functions, f and g, and we move them both by 5 meters to one side, that should make no difference to the preanna product of f and g should be the same as the preanna product of the shifted by 5 meter versions of f and g. On the other hand, if we take two test functions f and g and we move one of them by 5 meters to one side, then that should result in a different preanna product between f and g, between the transformed version of f and g than we have for the untransformed versions of f and g. We also have, we can discuss gauge invariance in this form by saying that if we take two test functions f and g and we apply some kind of transformation to the g, to the f that changes it in some internal way that makes no difference, then that is a gauge invariance in this formalism. So now I propose to discuss the axioms for quantum gravity as they might be in this kind of tentative approach. We have exactly the same as for quantum field theory. We have measurement operators, some finite set of such things that are nonlinear in these measurement descriptions, no longer on a Minkowski space, perhaps. It's not quite clear to me what invariances and covariances we should expect for the initial state. These things, well, I'm really unclear as to what we should require. Nonetheless, given a state, that will allow us to use the GNS construction of a Hilbert space. For quantum gravity, we'd expect there to be some form of spectrum condition and some form of microcausality. So if f and g are causally separated, we'd have commutation between the two measurement operators. But in quantum gravity, once there's non-trivial geometry at least, getting a spectrum condition and microcausality defined really well is something that's going to be rather difficult to do. Causality, as I said earlier, becomes this complex multi-path structure because of gravitational lensing and other kinds of geometry, doubtless. So I think it's helpful to introduce the idea of quantum non-demolition gravity, where we insist only on universal measurement compatibility. We don't require a spectrum condition even, because we're really going to work in a much more signal analysis inspired sort of way. So we have the FQND measurement and the GQND measurement commutes no matter what f and g are. Then, of course, that doesn't give us any non-commutativity, but we can introduce non-commutativity in some way or another, just as a transformation algebra using the kinds of techniques that we saw for CM+ in terms of a Poisson bracket. We can also just use the vacuum projection operator and so on. This is helpful because it separates out the two purposes for which h bar, Planck's constant, has been used, both to specify the amplitude of noise and to specify measurement incompatibility. And the second one is something that introduces rather a lot of trouble. And of course, quantum noise causality can be modeled explicitly in this kind of quantum non-demolition model. So now, Quantum non-demolition is something that in some talks I've introduced in the first half dozen slides. Here I've decided to do it right at the end, for better or worse. This box is most of the content of the slide number 40, for the Wigner characteristic function for a free field in particular, and for the Klein-Gordon and quantum optics. Both of these are positive frequency because of the theta k0 here. But if we look at signal analysis, we notice that negative frequencies are not associated with negative energy. There's no correspondence principle to require that in signal analysis. It's not quantum theory. So because it's not associated with negative energy, it's also not associated with instability. Nor is it associated with backward causality. It's merely what we need in the mathematics, so there is a real signal. So we would use something like the cosine of omega t plus phi, whereas for the analytic signal, we'd have the exponential of j omega t. And of course, this can be a very powerful tool when we're doing signal analysis. So in signal analysis, it's natural to remove the theta k0 from here and here. And if we do that, the non-commutativity term vanishes identically. So that gives us an everywhere commutative, essentially classical structure. What we might call a noisy classical stochastic field theory. The mathematicians might call this a random field theory, rather differently. And also, if we were doing quantum computing or quantum information, we might call it a quantum non-demolition field theory. But what we have here is not thermal noise. This is a Lorentzian translation invariant H-bar scale noise. Very definitely is not the same as the Gibbs noise, the thermal noise. And indeed, this is just as I described as the difference between thermal noise and quantum noise on slide number 16. So I can show you for quantum optics and quantum non-demolition optics really precisely what the relationship is between those two. For quantum optics, for the Gaussian state, using the preannul product on the previous slide, and these four equations, just as we saw earlier, which is enough to allow us to compute probability distributions. Because of the particular structure where we've insisted on positive frequency, we find that the commutator of the f measurement and the g measurement is sometimes non-zero when f and g have time-like separated supports or light-like separated supports. But for quantum optics, we can find an involution, by which I just mean that applying the same involution, the bullet involution, as I'm going to call it, twice, we get back to the same thing as we started with. And with an appropriate involution, we have, and we can satisfy this expression for all test functions f and g. Because of that expression is satisfied, we can construct an object, an FQ&D measurement, using the raising and lowering operators from quantum optics that is different from the quantum optics F-bullet measurement, because for the F-bullet measurement, the complex conjugation and the bullet involution would be in the other way around. Because of that change of order, we have that FQ&D and GQ&D commute always. It's effectively classical. Quantum non-demolition optics field is commutative algebra. But the Hilbert space is isomorphic to what we had for quantum optics because we started with exactly the same vacuum vector, exactly the same raising and lowering operators, and this bullet involution is an involution. Now, for quantum optics, I can show you precisely one particular example. It's not unique of the F-bullet involution, which in this particular case projects to the positive and negative helicity components, where we're using the Hodge dual, which is a complex structure on the bivector valued test functions that we're using for quantum optics. And it's essential there is a complex structure. If there is no complex structure, we can't do this construction as is. We can do this construction for the complex Klein-Gordon field, but for the real Klein-Gordon field, we cannot. So this is not something that can be done always for every quantum field theory. Right, so the thing with this bullet involution is that it is Lorentz invariant, because the Hodge dual is Lorentz invariant, but it's not translation invariant, nor is it local. That is not necessarily a problem, because both quantum optics and quantum non-demolition optics are Lorentz invariant. They're both translation invariant. And because they're both translation invariant, it doesn't matter, so to speak, that the relationship between them is not translation invariant. Because they are both Lorentz and translation invariant, we can't say, oh, quantum optics is right and quantum non-demolition optics is wrong. It could be the other way around as far as insistence on translation invariance is concerned. So now, of course, the quantum field theory, quantum non-demolition field theory, the algebras are not isomorphic to each other. The algebras generated by the Q and D measurements and by the F measurements are not isomorphic. But if we introduce an unrestricted Poisson bracket, or if we use the raising and lowering operators, or if we use the vacuum projection operators, then quantum optics can model many, many things. Anything that can be modeled by quantum optics, quantum non-demolition optics can also model as well. Essentially, that's because we've constructed something inside quantum field theory. The quantum non-demolition field theory can just use generalized probability that's available from its inclusion as part of quantum field theory. So now I have talked about signal analysis as if it's something rather more complicated than it actually is if you look in elementary textbooks. There's no probability theory typically in elementary signal analysis at least. If we add probability into signal analysis, then we get something which we quite likely would call a stochastic process. Stochastic process is not the same as quantum non-demolition field theory either. We need to make it 1 plus 3 dimensions, so it's much more like a random field theory in that respect. Furthermore, we want to introduce generalized probability because that's a useful tool for us to be able to use when we're doing engineering, and because we want to make close contact between the stochastic processes in this kind of way of thinking, we're going to make it an algebraic version of generalized probability. Finally, we have to add into stochastic processes the notion of a Lorentz invariant quantum noise. With all those things added, and it's really quite a long list, then we have quantum non-demolition field theory. Now, it is a long list, but all of these entries in this are things which I think with appropriate tutorials, a 19th century physicist would say, yeah, each of those steps is okay. And that is where we're going to leave that. What we have here is a construction that is rather similar to the de Broglie-Bohm construction for quantum field theory, where we consider the amplitude and the phase separately. But this construction is linear, quite differently to that construction in terms of phase and amplitude. It's Lorentz invariant, whereas the only constructions of de Broglie-Bohm for quantum field theory case, that as far as I know, is still the case. There is no Lorentz invariant version of that. And the other aspect of this construction is that it's more measurement theoretic. We're still working with Hilbert spaces. And so all of the tools of Hilbert space are exactly the same for this kind of quantum non-demolition field theory construction. Now, we can also compare this to consistent histories interpretation, which effectively does insist on commutativity at time-like separation as a criterion for constructing a consistent history. What we have here with quantum non-demolition field theory is a maximal consistent history interpretation, because we can have measurements everywhere in space and time, all of which commute with each other, and we can regard that as the history, if we like. Now, what this is not like is superdeterminism, because for one thing, this is generalized probability. It's not ordinary probability theory. Indeed, it's probability theory, which makes it not superdeterminism. Moreover, this is probability at all scales. It's not necessarily the case that the real world has noise emerging, bubbling up from all smaller scales. But the way that quantum field theory exists as a model, there is indeed noise bubbling up from smaller scales. As we consider smaller and smaller regions of space and time, so in fact the amplitude of the variance for an F measurement becomes larger and larger. So there's no question that there's no determination for this kind of quantum field theory, quantum non-demolition field theory. And indeed, this is not like superdeterminism, because what we're doing is claiming nothing more than what the measurement results are for quantum field theory, so long as we're also willing to consider the kind of operators that we can construct as quantum non-demolition field theory. So, as I say, we need a complex structure in order to be able to construct a quantum non-demolition field theory. Even if we can't do that, however, we still would need to be able to model situations where there are correlations at time-like separation. And so we might use something like the super-Heisenberg picture and something like the quantum non-demolition picture, the Bohr picture, the Einstein picture, or whichever name we choose. The Naimark dilation theorem is equally true for sequential measurements as it is for quantum mechanics. And indeed, even if we can't actually perform quantum non-demolition measurements, in which case we might say, well, we can't perform them, so they don't really exist. But we routinely discuss, for example, the momentum measurements we might perform for a particular particle, even though we don't have a diffraction grating that's infinitely long and so on. So really, in that kind of situation, we do as many measurements as we can to determine the quantum state as precisely as we can, and then we consider what the result would be for that experiment, for that measurement, if we actually were to perform it. And we can do that just as well for quantum non-demolition measurements. We can also now think about single experiments using largely classical intuitions. Of course, when we consider multiple experiments, we're going to want to use the tools of contextuality. So long as we internalize the consequences of quantum noise and contextuality, and also keep in mind that the analyticity might be helpful, might be better to use the quantum mechanics, quantum field theory, than to use the classical CM plus and quantum non-demolition field theory. Now, just to step back for a moment to quantum gravity, actually this is more about issues that are common to quantum mechanics too, and that is that now we should be thinking in terms of large language models and analyzing the information you might get from a journal article or from the supplementary information as a way to extract measurement descriptions in an automated way. Consequently, it's not just diffeomorphisms we should be considering anymore. If we have an English language description and a Chinese language description of the same experiment, the information extracted from one and from the other should give us the same predictions for what the measurement results would be, assuming they are equivalent. There should be translations from one to the other, just as a diffeomorphism is a translation from one coordinate system to another. Translation from one language to another is equally something which should be included in our worldview. There's also an aspect of formality and informality, where something that I can say to you may well hint at something which I cannot say to you in informal terms very easily at all. It won't fit into my spreadsheet. My spreadsheet requires data to be formal in a particular way, and what I want to say to you doesn't fit. Nonetheless, we should be taking some notice of that kind of partial or informal or inaccurate or imprecise information. And of course, formal and informal doesn't include everything either. Things that are in my head which I have no way of saying, even just in conversation, may be vitally important. It may be some aspect of how I use my fingers to precisely turn a knob in a way that I don't tell anyone because I don't even know I'm doing it. It's something that's become part of my physical being, so to speak, that is not part of what my brain knows of what I'm doing. Finally, I want to point out that coordinate systems, supposing we do use coordinate systems, those should be considered to be continuous. And that is independent of how the world really is. Even if the world is discrete, we can take two measurements and ask what the result would be given that we've done those measurements, we can ask what the result would be of a measurement that's 1/3 between the two measurements. That is something that gives us continuity in our imagination, in our heads, in a way that the real world may or may not be. And I'm not saying the real world is not continuous. If the world is continuous, of course, our measurement descriptions really ought to be continuous. If they're random fractal, then continuity will be helpful too. But if the world is discrete, it still would be useful, perhaps, to use continuous measurement systems, coordinate systems. So I'm going to say very little about quantum computing. I really don't know enough about it to say much. But what I will say on this one slide is driven by what I've said in the rest of this talk. As for any experiment, a computer just does what it does. Our description of it from a different continent, using quantum mechanics or CM+, or quantum non-demolition field theory will not make a difference to what the output of the computer is. But of course, it is nonetheless what we're doing with quantum computing, I think, is optimizing our hardware for a specific class of algorithms. Algorithms that don't run quickly on a digital computer as we're used to at the moment. What I think a quantum computing does, from a CM+ perspective, is, for one thing, it discretizes signals in an uneven way. It doesn't every picosecond with the system clock ask what the signal level is. It instead waits until the signal suddenly jumps and says, that's the time at which I now will report the time that that event happened. That is quite different from the way that a classical computer works with a system clock that is absolutely a taskmaster for the computations. We're also going to be using, in quantum computing, Lorentz invariant quantum noise as a resource. This is a language you will hear people use when they're discussing quantum computers. We're also going to be using a mathematics of matrices and so on that allows transformations between contexts, so that I think, it's not clear to me exactly how that does work as an optimization that allows us to do things that we could otherwise do with just a time-like evolution in a single thread computer, for example. All of that, I think, does add up to hardware acceleration. I'm by no means claiming this is complete, but from the perspective that I've established for CM+, this feels complete. And obviously for a specific class of algorithms again. What I think we can think of existing quantum computing textbooks and programming language as is, well, for one thing, they're unchanged. Quantum mechanics gives us programming languages. That is an abstract layer for what the engineer looks at, which is really a noisy signal line model. Quantum mechanics compute programmer is not worrying about what is happening on those signal lines, whether it's what particular physical implementation there is of that programming language. Equally, quantum field theory, quantum non-demolition field theory kind of feel like machine languages, which the engineer is going to be using to describe how the quantum and thermal noise is modulated and so on. So now we're getting very much to the end of this talk. We have started by considering actually recorded measurement results. So we've adopted something that is really quite classical in terms of just data. It's really quite close to Copenhagen, but it's more than Copenhagen because we've allowed classical to become something more than what Copenhagen considered to be classical without any contextuality, without quantum noise. We've also thought in terms of data and signal analysis, where the metadata, the window functions and test functions and so on, and measurement descriptions more generally, that becomes vital. At the extreme, if the data is provided to us encrypted in some ridiculously complex way, then that data is effectively useless to us unless someone tells us how to decrypt it. So the metadata tells us that kind of information. Of course, in a less complicated way, it may just be headings for a spreadsheet, for each column of a spreadsheet. That also is helpful metadata. It tells us something about the data. We can know whether it's real numbers or integers. That itself is metadata. It's something that would help a lot when trying to process data from some research group that's on a different continent. So we've introduced statistics and expected statistics. We've introduced classical measurement incompatibility. So we have classical mechanics, we've added non-commutativity, we've added quantum noise. That gives us a quantum ways of description, as always, but we also have a classical plus, quantum non-demolition, as a new type of description. And so this is not a distinction between types of system. Just because we can describe it different ways does not make it a quantum system or a classical system. That distinction goes away. There's no such thing as non-classicality. There's no such thing as the quantum classical transition if we allow ourselves to use CM+. Now, of course, it may be that it's helpful for some particular kind of model to have a quantum description for part of the apparatus and a classical description for another part of the apparatus. That may well optimize the mathematics, make it possible to do calculations that can't be done purely using generalized probability and joint probabilities and so on. As I said just a few slides ago, for CM+, measurement events now are thermodynamic transitions of a sort, for which, however, there are two types of noise. There's thermal noise and quantum noise now, and that hopefully will be enough to describe all the kinds of transitions that we call quantum transitions. I think it's important to keep track of the fact that quantum mechanics is an analytic form of CM+, in the sense that it allows only positive frequencies, whereas CM+ allows both positive and negative frequencies. Excuse me. So once we got to renormalization, I've argued that renormalization shows that we should introduce nonlinearity into the Whiteman axioms. The Reeh-Schlieder theorem allows us to show that doing that is enough to match the empirical success of perturbative quantum field theory. But as I said, that introduction is non-constructive. It's an inverse problem that is by no means straightforward. It may be decades, or it may be next year, that someone will realize a way of actually making the transition more straightforward. Now, I like signal analysis as a way to think about quantum field theory. I think it offers ways to rethink both the measurement problem and the renormalization problem. Even if you don't like my analysis, I think a future signal analysis might well help someone else to come up with something better. I don't think any other kind of approach is as focused on quantum field theory as this. So much of the interpretation of quantum mechanics does not extend to the interpretation of quantum field theory, and yet a signal analysis perspective really does make that quite a natural transition. Of course, once we come to quantum gravity, this kind of thinking in terms of data sets and signal analysis gives us a more empiricist kind of quantum gravity. We're focusing on measurement descriptions. It's more rigorous and more grounded way, I suggest, to construct interacting quantum field theory and quantum gravities, or the quantum non-demolition versions of that. So that's the end for now. Of course, this is incomplete. Of course, this is not a theory of everything. Hopefully, it's good in parts. Hopefully, there's some aspects of this that people will find helpful for their own theorizing in perhaps in mathematically much more sophisticated kinds of ways. Now, people have certainly said to me that this is too instrumental for them. But I think if you do want realism, quantum non-demolition field theory can be that for you, so long as you're willing to accept a sort of noisy at all scales classical realism. If you insist on determinism, on superdeterminism indeed, then I can't help you. You are on your own as far as I'm concerned. But even if you say, well, I'm going to take that perspective, when you're actually doing computational physics, you're going to use the more sophisticated mathematics of contextuality and a contextual measurement theory that is clearly preferable when it comes to calculations. Finally, I'll say that quantum and classical have been converging in my reading of the literature in numerous ways and for decades. This is surely an incomplete list of the kinds of mathematics that have been introduced in the last century, actually. So with that, I will end my attempt to explain quantum field theory with thanks for your attention, of course, and may you find something helpful in that.